Test, test. 1, 2, 3, test. Hallo, hallo, hallo. Zeg je? couple of seconds.
Раз.
Probably they will be broadcasting on Stripe again. But where do you watch it? You can come over. Either at home or I think there is Stripe S. They're probably going to be big screen Stripe S.
But how can you watch from there? Just standing on a square?
No, sitting on the ground.
It depends on the weather when you can.
Well, we can go to Stripe S. We can watch Stripe S. I can bring some
Покрывало.
покрывало. Can bring some
Food, some покрывало and beer.
You made it.
Yes.
Nice.
That's why you gotta. Hi.
Hi.
I have a second.
You always got them.
No, man. Look to the end. Look to the end. You are the main star. I mean,
How do you see this?
doing this video.
I saw it, but not.
Someone of you with me and.
What did you put in the end? If room? You're kidding?
I don't think so. No. Anyone is going to if room?
Wow.
Do you know who's volunteering if room? You are the main star of the video.
No,
I think I may have put you on. No, you haven't been volunteering yesterday.
No.
I have a second video. I need to post it.
You can fake it. You do the movie now and you put it.
Let's do it. Let's one time now.
Moderator Simon.
The budget.
Casper. Who's Casper? You can ask in chat. Casper.
Some random.
Okay.
Want some
Probably going to
cinematic effect.
Yeah, I use it. But then sometimes.
No, I'm gonna send to you. Do some cinematic.
But it's fine. I think we will show us.
Cinematic work.
Otherwise, we will hold the microphone to ask the question. That's the rule.
But there are some other things you can do now. Pour pour water to people.
Where are you guys from?
Originally from Russia. He's Italian.
From?
Russia. I mean Rusland.
And he's from?
Italy.
Italy, okay.
Would you like something? Yeah. 10 minutes.
Okay, 10 Italian minutes for Dutch one or
Yeah, there's a difference.
what's 10 Italian?
10 Italian minutes is about 25, 30, 40 minutes. 10 Dutch minutes are 9 minutes.
9 minutes.
Yes, they are like generally urgent.
I think
Russian minutes?
10 minutes.
You
It's
also
10.
Russian?
Yeah. 10.
10 minutes, 10
It's
Russian
10.
minutes?
Yeah.
You're
And
not
you
going-
arrive after 20.
You're not going back after this, are you?
No, I hope not.
You don't live there anymore.
No, I don't. And yeah, well, I mean, I can go back to Russian, but they will immediately deploy me in Kiev or something. So fuck that.
How long did you live?
Here I live almost 5 years. Yeah.
And you live here now?
Yes, in Napoli, yeah. So I did my PhD in TV at the Napoli University, and then I started the company together. So working on it. Yeah.
My passport is very simple. Straight NATO. I expect to. And you're also from Russia?
Yeah.
But he speaks well. Can you show us? I never saw it.
No, he speaks Dutch well when he speaks to us. I'm not sure how he speaks Dutch.
And you never bothered to learn Dutch?
No, of course I bothered many times. Yeah,
You
I even passed the exams on Dutch. But
the thing is, if a foreigner tries to learn to speak Dutch, then all the Dutch people speak English.
Yeah.
So if you speak Dutch with some dialect, you automatically start English.
exactly. So I never get
How did you?
I never get a chance to speak to my neighbors. Like I was like trying to talk to them. Sometimes they give me like 2 seconds and then yeah,
There is a life hack. Flams people, they do the opposite.
Yeah?
Yeah. You start speaking them in English and they switch to that.
Oh, all right.
And it's actually a very good
so you
life
need to
hack.
go to Belgium to yeah.
It's a bit
practice.
different.
Okay.
Well, I know that Dutch people speak English.
Perfect English. Yeah, so it's. I think there was like 5 years ago there was even some statistics showing that average Dutchman speaks the grammar of the average Dutchman in English is better than in US.
Yeah.
So Dutch people, the grammar of Dutch people is better than in US.
Because in US they speak Mexican.
Yeah,
Spanish.
the Spanish. So that's true. And are you from Eindhoven?
Yeah.
Good, nice.
So when we see in television and in the radio that it's all English.
Yeah.
Oh, we watched football yesterday. It was Dutch.
Of course.
Yeah, well, that's something else. But we don't translate movies and things like that.
Yeah,
So in
that's
Italy,
true.
they,
Yeah.
and in France and in Germany, all the US
Content. Yeah.
content is translated into their language. And we have to use subtitles.
Translated in
Yeah,
the
that's
Dutch.
true.
Oh yeah, really?
We are 60 million, 59 now. With 1 million left to move to the Netherlands.
Jerome asked me for a volunteer at the reception desk.
Oh yeah.
Should I go?
Yeah, you can go.
Yeah, you go.
We go there.
I mean, but I will return because I need to post the video.
See you later.
See you.
So a lot of Russian people here.
Yeah.
Right?
We
That's
we
just
know
the
why.
three of you.
Yeah.
No more.
I mean, in Eindhoven, yeah, I think like in Lesbian Chinese. Yeah.
There are some and Ukrainians.
And Russian where? Where in Russian did you?
From different places. I'm from Vladivostok. It's like all the way close to North Korea, like Japan side.
Wow.
Yeah, it's
Yeah,
far.
far,
Yeah.
far. Yeah. Me too.
I haven't been there. I've been to Moscow. And, uh,
Sparking is too much for that.
Yeah, I used to come up with something to drink of. Have you
How
been
about
able to
the
go
open
to?
tour?
Yes, it's in yeah, I've been there
Yeah,
with the museum. What's it called?
Mhm.
Hermitage.
Hermitage. Yeah,
In St. Petersburg.
Yeah.
yeah, St. Petersburg. Yeah, I've been there.
Mm.
Not so long ago. Well, pre-corona.
Uh-huh.
When we did it all.
Uh-huh. Oh, nice.
It was always a weekend with my wife.
Mm-hmm.
Work for work.
Yeah.
It was nice over there.
Yeah,
In
it is.
winter time, so a week for Christmas was beautiful.
Mm,
Yeah,
yeah,
that
it
was
was.
cold though.
Yeah, but well,
The St. Petersburg is really cold, actually.
yeah, but for weekend
Yeah.
holidays, it's well,
It's okay.
Yeah.
It's fine.
you don't have to sleep outside.
Yeah.
It was nice, snow and lights everywhere, Christmas decoration. That was beautiful.
St. Petersburg was built by Peter the Great, and he actually used to live in the Netherlands for many years,
Oh,
and he loved the Netherlands, and he decided to build a city which reminds him about the Netherlands.
here, what city it was?
The St.
St.
Petersburg.
Petersburg. Oh, okay.
I mean,
It's like this
it's like a
general.
blend of Russian and Dutch, at least
Oh,
his vision.
I didn't know that. Otherwise, I would have looked with
Yeah.
different eyes. But I don't see any
Similarities.
similarities.
I think there's channels
Yeah,
that
some like
people.
canals.
Yeah, well, okay, but that's
Yeah, but when I
not.
visited Paris, I thought that maybe it's more similar. I mean, the Sena, like the Loire in St. Petersburg,
But
it's more similar
no,
than
it's like St. Petersburg is extremely different from any other city in Russia. So, and he brought it from the Netherlands.
Oh, okay.
And he even has a museum in
Anna,
Zantan. It's in
Anna,
Zantan.
yeah, Zan or Zantan.
Zantan.
Yeah, they have his house where he came from
Mm-hmm.
Russia here. So he wants beside the
Beside it.
very beside the house he built ships. So he lived in a small village in a small house. So he was trying to gain the idea how to do that. And they have a museum in Zan. It's like for his like his owner
Yeah, in his honor.
in his honor.
It's a small museum.
Okay. Thanks for the lesson.
Yeah. He is like sort of, yeah, one of the kind of big figures of the Russian art.
He's great.
He's not a Tsar,
And they don't call them tsars, but he was emperor actually.
In Paris.
emperor. Yeah. Not long ago.
And your families are still in Russia?
Yeah.
Unfortunately, yeah, but they're gonna. I mean, my parents are old enough not to move. Kind of, they don't want to. I mean, it's just a bit hard for my dad. He's like in. Yeah, he will not give up his routine. You know, like he's
Mm-hmm.
going hunting and like all the kind of stuff. And my brother, yeah, he's 40.
Yeah,
So
he's living in St. Petersburg.
yeah, he lives in St. Petersburg. So for him, yeah, I hope that at some point he will escape the.
And how does the Ukraine war influence their lives?
Uzbekistan, Serbia, Kazakhstan.
Russia,
Turkey.
China.
China is not easy actually to speak Chinese. Yeah, but
North Korea.
that's probably
Now they
easy.
have excursion to
Yeah, yeah. Now they actually have tours to North Korea. So yeah, it's good. But yeah, Thailand like is Asian country, so wherever they could go, anywhere.
So Turkey and all that is not all.
Turkey as well,
Turkey is
actually.
very popular.
Yeah?
Yeah, yeah. But Turkey is expensive for most of Russia. Yeah, yeah, for sure.
The standard of living is lower than here, or
Like in where? In
in
Russia?
Russia?
I think
It's
yeah.
not, I'm
I
not
mean
with
if
zero.
yeah,
per month.
no, I mean not that bad, but
It can be that bad.
yeah, it can be that bad, but on average,
100 per month.
if you exclude Moscow, then
Yeah, okay, Moscow is a very
but
good.
Moscow
Outlier.
is just an outlier. It's totally different.
Yeah.
The wages there are good, and people are can earn enough. But like for instance, in my hometown, the wage, I think the average salary would be
No, they said that average salary is 560 euro.
560. So you can
560.
imagine what's
Unemployment, is there people unemployed or not, or
That's actually very.
that's a good question.
We actually don't have a lot of unemployed people,
They
but
don't
that's
do the
that's a bit wrong statistic because a lot of unemployed people they went to war.
War or they left. So
Yeah,
like
yeah.
especially people in IT sector, like IT, like software engineers, they just escaped. So of course there's there's
Yeah,
not
so
no one to
yeah,
employ.
if you look at the number, it's very low, but that's because those people are just
Yeah.
fighting. That's also not an accurate rate, of course.
It's like 4 million people unemployed. But then you can compare salaries for people who are volunteer in war. It's 2,000 euro. And for average salary when you're just living in Russia and working, doing some stuff, it's 560.
but
Imagine this
yeah,
difference.
but shopping and everything and clothes and house rents are also 25%.
Hi.
Yeah, I think so.
Are
Maybe
you going to
more.
be a speaker at this session?
I
No.
would say
Okay.
that people are still welcome, but it depends on the flexibility.
I am a speaker. Hi. Hi. Michael.
Yeah.
Yeah. Albert. I will be the moderator. Okay, great. So
Can I just test my laptop on there just to make sure I can?
yeah, go
get
ahead.
the thing working?
You're second speaker.
Yeah, well, although there's some sort of 10-minute thing at the beginning,
Yeah, there
right?
will be a small talk in the beginning. Yeah, but he's going to be the next speaker, so he just wants to check
Oh,
his.
Yeah. I just wanted to check the HDMI, make sure.
Do you have audio in your presentation?
No.
Cool.
Oops. Just me. Okay.
Are you planning to walk around when you present, or you'll keep static? So
I'll
just,
probably just stand here, I think.
because the camera, as far as I understand, if you go somewhere here, the camera doesn't see.
Don't worry, I won't run that far, for sure.
Let's stay here.
Yeah, okay. So you can see all that and everything is flying by and nobody, no problems. Okay, I just wanted to make sure. So, since I didn't have time to upload anything.
So, there's a few things. 5 minutes before the end, I will show you
Yellow card and red card, very appropriate for the stadium. I like it.
Yes. So
I think I might steal that idea for my.
It's going to be like time to kind of wrap it up, because like red card, it means that
Yeah, you're gonna,
get
like-
our like last question, and so the next speaker should start connecting.
Yep.
Basically, when you see a red card, you should come and connect your.
When I see you give the previous guy the red
Yes,
card,
yes,
then I will
exactly,
come.
right.
I will substitute onto the field.
Yeah,
Okay.
yes, yeah.
Alrighty. Water.
Yeah.
Is this for us or?
Yes, it's for you.
Okay, and the blue and the red indicate.
So this is still water and is vodka.
I figured that's what it was.
Maybe some people will want vodka instead.
And vodka.
Should we put some here as well?
Yeah.
Yes, there's water.
Yeah. It's. I'll go find a place for this guy.
Two glasses.
Yeah.
over here.
as well.
And is there a lot of differences with Vladivostok and
No, there's just some one language spread all over.
so no dialect?
No dialect.
Yeah, it's 4,000 kilometers away.
Exactly. Yeah.
Oh, that's different here.
Yeah.
You go a little bit in
Yeah,
Belgium.
next village is one dialect.
Yeah, that was one of the most shocking things when I moved abroad. I mean, I also lived for a couple of years in Japan, and there it was also similar. Like you go a different city and everything becomes some words you never heard of. So,
Have you tried to pick up Japanese as well?
yeah, and I was actually succeeding because better than here because they don't speak English at all, so you have to.
I know, I've been there a couple of times.
Yeah.
And the people I had to work with, they speak English, but aside from that, none.
Wait, this is our first speaker, Herman. Okay.
Here.
From there.
Do you have audio in your presentation?
No.
Good. That side. The good on power?
What?
The good on power?
Yes. Yes. Should be good.
Well, I gotta get my.
Want to keep that on?
Yes.
It's switched on already. I have it close there.
Ah,
Put this.
I will be sitting here, just.
perfect.
And when you're done, the next speaker gets your mic, so you have to hand it over
Okay,
to the next
perfect.
speaker. Try to stay here, or at least there, because if you don't, you'll walk out of the camera image.
Ah, okay. Okay.
Are you comfortable?
Yes.
I'll open it there.
Yes, and I want to see if the cursor is
Why
is
is it
seen
not?
on the screen.
It's not turned on. Is it?
Can you try with this computer to see?
Yeah.
Maybe.
Oh, it's I left it out. Let me switch on the projectors go out if they don't get an input.
Okay. Yeah, I'll introduce you and then you can start. So I think we'll start like in, let's wait for some other people to come and then I think we'll kick it in and at 11. So it will be 10 minutes delay.
Okay.
So, is this shift for all tracks or is it just this one? So the 10 minute shift?
I think it's for this. Hopefully.
Yeah, because we need to switch tracks.
Huh? Hey. Hi. Yes. Great.
Are you speaking at this side as well or not? Hi. This is Jules. Hi. Are you speaking at this side? Hi. I'll be moderating. So, are you? Okay. And start now. Are you? Start. Oh yeah. I said it. I do. Alright. Talk to my mom. wait for a couple of minutes, okay? And then start. Yeah, I think so.
This is,
Couple.
okay.
Right, a couple of minutes, okay? Please start. All right, cool. So let's kick it off. Our track. So our first speaker will be Herman, all the way from Buenos Aires. So he'll be talking about his work on SkyML, specifically on the model called Goku UI. And let's hear what Herman has to say, and let's give him a round of applause. Our first speaker, good luck.
Thank you very much. Okay. Well, hi everyone. My name is Germán Abrevaya. I am a physics PhD student from University of Buenos Aires. And today I will show you an example of how we started with a given SciML model and improve it to the point to be able to handle one of the most complex systems in the world, which is the brain. So, as you know, this work is in the context of SciML. And in particular, we've been working with latent differential equation models, which you can think of as some kind of variational autoencoder with differential equations inside ruling the latent space dynamics. Specifically, we work with a model called GokuNets, which, as in any autoencoder, the goal is that the output reconstructs the input as close as possible. And in this case, the inputs are high-dimensional time series. Initially, each time frame is processed independently, usually reducing the dimensionality. Then they are processed sequentially for learning the parameters and the initial conditions of a differential equation, which is explicitly provided, allowing you to incorporate some prior knowledge about your system. Then the equations are solved, and lastly, the trajectories are transformed back to the original space. So as I told you, we wanted to apply this to neuroimages. And we use resting state fMRI. And for the differential equations, we use some Stewart-Landau oscillators, which is a well-established model for neural ensemble dynamics. The issue with these models, and in general with differential modeling, is that for training them, you have to differentiate through the solver, calculate gradients with respect to the initial conditions and parameters, which tends to produce a quite complex loss landscape. And in turn, this can make the training a bit challenging. So it is well known that even if you have very simple oscillatory data, training a neural ODE on this data can be stagnated on this kind of local minima. One possible solution is to use a multiple shooting training strategy, which consists on splitting your time span in multiple shorter windows and impose some continuity constraint between the windows. This was already implemented for neural ODEs. Actually, these animations are from the defect flags documentation, but we extended it for latent differential equation models where you don't have access to the ground truth initial conditions for each window because the differential equations are happening in the latent space. But you can still try to impose the continuity constraint. So we developed a multiple shooting training strategy in the latent space using multiple initial conditions, but a single shared set of parameters for all windows, and added a regularization term in the loss function. In addition, we added an attention mechanism to the part of the model that learns the parameters, which originally was this bidirectional LSTM. So to the GokuNets, with all of these enhancements, we call it Goku with ubiquitous inference, or in short, Goku UI. So now let's see in detail all of these enhancements. Let's start by recalling how a traditional bidirectional LSTM works. So you have your time series, and you have one LSTM processing it forward in time, another LSTM processing it backwards, and the final output is the concatenation of the last output from each LSTM. on the other hand, on our attentional by LSTM, you keep all the outputs from both LSTMs and do a linear combination of them weighted by some attentional scores. So now let's see a toy example of the multiple shooting. So you split your time series into multiple overlapping windows, and then you have one LSTM processing all the windows. And eventually, their outputs will end up being the initial conditions for the different multiple shooting windows. And then by using the parameters that are before, you integrate all of them in parallel and add a regularization term in the loss function, quadratically penalizing for the differences between the initial point of each window and the last point of the previous one. We evaluated this on two datasets, one synthetic and one empirical. For the synthetic one, we use 3 coupled stochastic Stuart-Landau oscillators and enlarge the dimensionality so that we had some high dimensional inputs for the model, which were actually sourced from a known low dimensional dynamical system. For the empirical data, we use resting state fMRI, the time courses of an ICA analysis, and inside the GokuNets, we use 20 Stuart-Landau oscillators. We evaluated this on the reconstruction task, but also on forecast task, because for all of these models, you can continue integrating the equation farther in time beyond the reconstruction limit in order to have some forecast of the future activity, and compare them against a few baselines. So let's see some results. Here you have the result for simulated data. These are the reconstruction error on the left and the forecast error on the right in function of the size of the training dataset. And keep in mind that all the axes are in logarithmic scale. So we can see here that already adding the attention mechanism, which corresponds to this orange line, the reconstruction improves with respect to the plain GokuNet in turquoise. If you trained with multiple shooting, this green line, it improves even further, but the best overall performance is achieved by Goku UI, which is a combination of both mechanisms, which is this purple line, and which achieves a threefold reduction in reconstruction error compared to the plain GokuNet. And also it displays very good data efficiency, achieving its peak performance with only 300 training samples, surpassing other models which were trained with up to 16 times more data. On the forecast task, we see that for very little trained data, the VAR, the vector autoregressive model, surpasses all the other models, which is expected because in general, statistical models are expected to surpass machine learning models when you have very little data. But if you have more data in your training data set, then you get some similar results similar trends than in the reconstruction. These are some examples of the reconstructions on the test set, and here we see that the reconstruction from Goku UI are much closer to the ground truth than the plain GokuNet. On the empirical data, we see again we have reconstruction on the left, forecast on the right, and we see that in this case the attention mechanism didn't improve much the results, but the multiple shooting did, and very significantly. And actually, Goku UI achieved a 5-fold reduction in reconstruction error compared to the plain GokuNet. And on the forecast side, again the VAR got the best result for the very beginning of the forecast, but its performance decreased very rapidly, and then Goku UI take the lead and get the best performance, best forecast performance up to 15 seconds ahead. And lastly, also these are some examples of reconstructions from test subjects, and we can see that again the reconstruction from Goku UI are much closer to the ground truth than the plain GokuNet. So, in summary, we significantly enhance the GokuNets, or you could say that we increase Goku's key by adding some attention mechanism to the part of the model that learns the parameters, and develop a multiple shooting training strategy in the latent space, using multiple initial conditions, but a single shared set of parameters for all windows. and the regularization in the loss function, penalizing for the discontinuities in the latent space. And by doing this, we increase the performance and data efficiency on both reconstruction and forecast tasks on simulated and empirical dataset. And moreover, we were able to encode the whole brain dynamics into a latent, low-dimensional, and interpretable dynamical system, which we will try to leverage for getting some neuroscience insights, such as functional connectivity or doing some classification on mental states or conditions. Well, this is all the amazing people who contributed to this work. And you can scan this QR for getting access to the full paper, the codes, and also for a specific ChatGPT instance that is expert on our work and will hopefully be able to answer all of your questions. Thank you very much.
Yeah, are there any questions for Herman? No questions from the audience? Yeah, then I'll have just one question. We have time exactly for one question. So you've experimented with the brain scans, right?
Yes.
Like then where do you see it can be applied also besides like brain scans? Did you think about it? Like are there any?
Yeah, it is like a very general machine learning architecture.
Yeah.
So and you can change the differential equation for any other type of equation. Actually, that is one of the advantage that the Goku nets were originally in Python, and just by coding it in Julia, we can leverage all the power of the SciML ecosystem, and you can use any kind of differential equations. So if you have your particular system of interest, you can try to guess some underlying equation that rule the dynamics, and even combine it with neural network terms such as like in the case of universal differential equations, but inside an autoencoder which learns the
Awesome. Space. Yeah, great work. Let's give
Thank you.
a round of applause to Herman.
Thank you very much.
Okay, so next up we have Ayush, software engineer at JuliaHub. He'll be talking about symbolic indexing interface.gl. Yeah, so let's welcome Ayush. So, yeah, and then, yeah, just Frank will help you with.
Okay.
Yeah.
This clip here somewhere.
I don't think is the screen disabled right now?
Okay, I'll open it in a second.
Okay, I see.
Did you get any?
This one usually does work. I mean, I use it for my office work. I can try that. It's not
Should
showing up.
recognize both
Yeah.
screens.
Okay, yeah.
Can you send it?
I've uploaded it on the Bitlex site.
Do you have it there? I don't know.
I don't think so.
You have it on- you can put it on the USB if you want.
Okay. seem to. It's not recognizing this, is it? It's weird. This worked till yesterday. Yeah. Maybe it's.
Frank, can we try again? Maybe with this laptop. Let's see.
Yeah, I can't send my presentation. It's not recognizing the USB
Yeah.
drive. I've uploaded it onto the site, the Pretlex site.
I don't think there is an access here. So, but I think there is something is off with.
Where's my second?
It doesn't detect either.
And the resolution is
I think we'll run it from here. It's just a matter of first day.
Okay, that's turning on.
Maybe we can try to reconnect there again. Oh yeah, it got it. I think. Yeah, no rush. You'll have all the time you need. But yes.
I don't know where my presentation went. That's fun.
Disappears somehow.
Oh, wrong presentation. So it was. It's not here. Still the wrong one. I'm sorry, I'm not sure why this is opening the wrong presentation. That link usually works.
I still see there are glitches.
Okay, yeah.
Let's try another one.
I think we can just remove this.
Well,
Okay.
let's hope it's all good now.
Yeah.
Yeah, you'll have enough time. So.
Hey, thank you everyone for bearing with the technical issues here. So I'll be giving a talk on symbolic indexing interface, which is a library I've been working on that is part of SciML, and it's used extensively throughout the SciML ecosystem, specifically for the symbolic indexing workflows that are provided with modeling toolkit.jl. So I'm Ayush. That photo was taken yesterday. And so these are my GitHub and LinkedIn, and you can reach out to me on any of the platforms there. I'm fairly active on the Julia community Slack. I keep an eye on it. So, and well, I've been working at JuliaHub for since 1 year now, and all of that you see is like 95% SciML there. And a lot of it is actually centered around symbolic indexing interface, which was something that really came into play in the ecosystem around December of last year. So before I go into what symbolic indexing interface actually is, I'll just give a quick overview of symbolic indexing. So just a quick show of hands. Has anybody here used Modeling Toolkit before? Okay, so quite a few people, yeah. So what symbolic indexing is well, you have something like this sort of model. It's a modified sort of Lorentz system from the documentation, and so you create the model using Modeling Toolkit, and your variables are called X and Y and Z, and you create the problem and you solve it. And when you solve it, you get this sort of solution object that, if you notice, has like 4 elements in each element of the time series. And it's not really apparent, I mean, because I created 3 variables, and somehow I have 4 things in my time series, and I don't know which one goes where. And so that's where symbolic indexing comes into play, because from the user, you really don't want to know what X is, whether it's part of the time series or not. And even if you ask for some sort of computed quantity like X plus Y, you should just be able to get it. And that's what symbolic indexing enables you to do. That instead of accessing the solution at specific numeric indexes, you just give it the variable you're looking for, and it does everything behind the scenes. So that's from the user perspective, and it actually has some benefits for developers as well. So with Modeling Toolkit version 9, we changed how we represent parameters by default. And it's now this really complicated struct, the display of which I've actually just cut out for both of our sanity. And well, it actually contains all the parameter values, and the way that the data is laid out is completely prone to change with versions of modeling toolkit. But because we have symbolic indexing, there's a layer of abstraction between them. So we can translate the parameter sigma into whatever index it has in that complicated data structure, and you just get out the value that you ask for. So I'll go over why this library was necessary and the sort of problems that we had with symbolic indexing in SciML before. This is the old sort of package hierarchy where you have all of the modeling libraries, the DSLs at the top level, like Modeling Toolkit and Catalyst and other libraries that build upon it. And then you have the low-level sort of stuff that actually does all of the, implements the data structures of your solution and problem and does all of the symbolic indexing. And the problem here is that the top-level libraries are the ones that know what are the symbols involved in the system and how do I get them. But the actual values are accessed through the lower-level libraries. And so you sort of need to provide flow information in both directions, where the top-level libraries need those data structures, and yet the data structures need information from the top-level libraries. And so we ended up with having multiple ways to do the same sort of symbolic indexing workflow. One of the primary ones was if you've ever used ODE function, it has a couple of fields called sims and in-depth sim and param sims, and we just populate them with a list of symbols that are in the system. So like this, these are the variables, these are the parameters in my system, and this is the independent variable. And that is what allows you to do symbolic indexing. So if I ask it for sol of :x, it'll just give me that value. And there are downsides to this, which I'll get to later. There's also another sort of approach, which arguably is a little hacky and not very extensible, is labeled arrays, where they're just a wrapper around normal arrays or static arrays, and you can just associate a symbol with each element of the array. And then that you can access that element with that symbol. And then supporting this in the solution data structure is another sort of very, is an implementation that really was prone to breaking and not being consistent with everything else. So what all of this led to is implementation inconsistencies, where there are different sort of type hierarchies, and they both implement symbolic indexing in slightly different ways. And you end up with things like this, where if I ask for the time series of x, y, I get a vector of vectors. And if I ask for the time series of x, y at all time points, so that's what the colon represents, you get a matrix for some reason. And specifically, even in sort of similar data structures where you have like an ODE problem or an integrator and a solution that doesn't have a time series associated with it, the data layout for all three of them is practically identical. And yet the indexing functionality for all of them is implemented completely differently, and they all have edge cases that one handles and the other doesn't. And it led to a lot of bugs and a lot of issues in the SciML ecosystem, where somebody was confused why they can access some variable here and they can't access another variable there. We also ended up with things like implicit circular dependencies. So, for example, this code snippet is from SciML base, which doesn't depend on symbolics or modeling toolkit, and yet if you notice, these little subscript pluses are what it uses to like search through all of the symbolic variables, because those are a symbol that is very specific to symbolics.jl, and if symbolics ever changes that in the future, which it can do, because it's not really public API, this just would completely break without anybody really having done anything wrong, for the users at least. There's also other sort of problems where if you did symbolic indexing in a hot loop, so for example, in this sort of code snippet, the goal is to optimize an ODE problem solution against some known data. And if you're updating the value, while updating the value of some initial condition or some parameter, and each time you do this update, it would look up the index of that symbol, and then it would access that value and update it. And that index lookup is actually really slow. And when you're calling this function like hundreds of times a second, it really slows, contributes to the runtime of your problem. Another problem, and you can see that's a very long list here, is this tiny little function called isSymbol-like, where it's defined in recursive array tools for identifying what symbolic variables are, because they don't really have a common subtype and they don't really have any sort of common data layout or a common trait. And so it's extended in some places, and it's imported through like multiple transitive dependencies in other places, even though it's not like it was imported through SIML base, despite not being part of the SIML base API. And we had a lot of these sort of just hacky implementations of pulling functions from nested dependencies and that kind of stuff that we just wanted to really just clear out. And so symbolic indexing interface is the solution to all of our problems, if I could say so. Where with the library sort of being added, this is the package hierarchy that we get, where so symbolic indexing interface has an interface, as the name would suggest. And the top level libraries will implement part of the interface that tells how to define, get indexes from symbols. And the data structure libraries, SIML base and recursive array tools will implement the interface that allows translating all of these indexes that you get from the symbolic variables into actual values from the data structures. And all of the indexing is done in symbolic indexing interface. So what happens there is that since we have one sort of common implementation, everything just works exactly how you want it to. So this is what I mentioned earlier, an interface for what symbolic indexing interface calls index providers, which translate symbolic variables into indexes. And one of the main goals for designing this interface was being able to get the index of a variable without actually having to search through a list of variables with like find first or something, because that obviously doesn't scale when you have like hundreds or thousands of variables in a system. And there are also other sorts of metadata queries that are associated with this interface. Then there's the value provider interface, which turns these indexes that you got in the previous step into values, which could be a time series of values. They could be a single value, depending on the sort of data structure that you're indexing. And the interface is consistent across all of these types of data structures that will give you values if you give them indexes. And what this enables us to do is something like this, where the getU function will automatically generate a getter given a system and a variable in that system. So it has heuristics to identify if it can just directly index the data structure, or if it needs to, for example, generate a function that will that when called will return the values that you want. And it's capable of handling like completely nested data structures. So as you can see in the second column, I can ask it for an array of what modeling toolkit would term observed quantities. And it even works with tuples, and we can have mixed sort of index types. So one index is a symbol, the other is a symbolics num, and it just knows how to handle all of this, and it does its best to ensure type stable indexers. So like those inferred tests are actually part of the test sets, and we make sure that they're all type stable as much as possible. And it handles very nested data structures as well. So if I had an array of arrays of tuples, it'll just figure it out. And it even allows for indexing multiple different data structures as long as they're associated with the same system. So if you notice, I just created one getter at the top, and I can use that same getter function with the problem or with the solution, or I can even use it to access the solution at a particular time point. And it knows what to do. In a similar vein, we have automatic setters. So if I can just generate a function to set a particular value in a problem. So this specifically works for things that are not solutions. And it can set like, it has basically the same semantics as the getter functions, where it can handle nested variables. It will handle different types of symbolic indexes. It even handles actually directly indexes. So if I give it 1, it will update the value at index 1. And all of these also have been confirmed to be type stable. We maintain that sort of testing functionality. Another really cool thing that this does, and it makes it consistent across the entire SciML ecosystem, is that if you want a DSL and you want to do it without using modeling toolkit, you can just use this symbol cache data structure that symbolic indexing interface provides. And you give it the symbols, and it will automatically be able to query them for all of the indexes that it needs. It will cache them into a dictionary, so it's an order 1 lookup instead of having to search through all of it. And if you give it a dictionary instead of an array, so your indexes don't really have to be integers. They can be absolutely anything that you want them to be. Modeling toolkit, for example, leverages this, where this index into its parameter object is not a numeric index. It's a custom struct with unknown internals, basically. And if you use symbol cache, you just get all of the indexing functionality for free. And if you use symbol cache with symbols, you even get the ability to sort of generate functions for expressions, which you really couldn't do before this library existed. So if I just have x, y, and z here, I can ask for x plus y times z, and it will figure out how to get me that. We also have standardized implementations for maybe less common but still very useful workflows, where, for example, you might be optimizing variables that are common across multiple systems and multiple ODE problem solves. So in this sort of contrived example, like x and y are common across both systems, and I want to optimize, let's say, x, y, and z across one system and x, y, and w across the other system. So SI is intelligent enough to figure out that x and y are common, so I only have to return a 4-length array. And if I give a 4-length array into the setter function, it will update x and y in the first one and x and y in the second one from the same array elements. So you both reduce the memory consumption, and you don't have to maintain that if the same variable occurs in 2 places in your array, those values have to be the same. We just handle that for you. One very recent addition that is actually getting support throughout the ecosystem, it's sort of in process, is support for multiple time series. So on the left, the example is a model which actually has a discrete sort of subsystem associated with it, where all 2 discrete subsystems actually, where one will update every 0.3 seconds and the other one updates every 1.1 seconds. And the main continuous system runs on its own. And so you have like multiple different time series. So you have the continuous time series, which the solver determines is 74 lengths according to how the stepping works. We have the 0.3 second time series, which has 17 elements, and the 5-element 1.1 second time series. And SI knows how to handle all of these. So it will even error like very nicely, saying for example, if I asked for UD1 and UD2, it would very clearly tell me that these variables belong to different sort of time series, and I can't access them at the same time because the length of the vectors are not identical, and they're completely disparate. So it has all of that, all of those checks, and with appropriate error messages. So you really don't have to run into an error message and not know what it means and why this sort of indexing functionality is not working. And the result for all of this is, for one, pretty greatly improved performance. So this is a very quick benchmark that I whipped up, where for a system with variables ranging with the number of variables range from 5 to 100, I just take the minimum time to index each variable in the system and average all of that for each system. And so for before symbolic indexing interface, or the latest major version, this time sort of scaled very significantly with the increasing in size. And this, for example, has an impact in the optimization hot loop, especially if you're accessing multiple symbolic variables. And now with the number of systems, the time is actually practically constant. And what is even better is something that I'll show is that you can just cache those getter functions. So if I'm updating the same variables in the hot loop, I don't have to do that translation step twice. As long as I have that getter function, it's serializable, and I can just reuse it and not have to worry about paying the cost for index lookup multiple times. We also get some developer flexibility, which is something I touched on in the very beginning of my talk, where, for example, these are internals of the MTK parameters struct that Modeling Toolkit uses. That's very prone to change, so it's just an example. Please don't rely on it. But all of these fields could really be anything, and they have actually changed 2 or 3 times throughout the development of the tool. But for users, they don't really care. They never have to interface with the internals of the struct, and we're free to change it however we want, because we know users will ask for symbolic variables, and we can handle where that's located inside this data structure on our own. And we also get all of the nice things that were basically just problems before with SciML, where we don't have any more circular dependencies, where sort of the lower level libraries need information from the top level libraries, and data ends up flowing in the opposite direction that you really want it to. And there's a single consistent implementation that we try our very hardest to make it as fast as possible and as type stable as possible. And another really cool thing is that the symbolic indexing features are independent of the symbolic backend. So if you have your own sort of mini DSL that doesn't even use symbols or symbolics.jl, if you implement this interface, everything just works. It'll know how to do and how to handle your expressions. And of course, the advantage of having cached getters and cached setters is that you can efficiently access the same symbolic quantity multiple times and get the same result without paying the index lookup cost. Thank you. These are the links to SciML and specifically the SII library for reference. If there's any questions, I'd love to take them.
Yeah, I see a few questions.
Okay.
I think this one first.
Sure.
Hi, thank you for your talk. It was really interesting. My question is, you mentioned that it is possible to kind of index through variables having different types of time series data. Would it also then, so let's say we have such a solution with a different time series, would it make sense to somehow get an interpolation rather than throwing an error when these time series don't match?
Okay, so I'll just go back to that slide. Yeah, so the thing with discrete, specifically like mixed discrete continuous systems is that these clocked variables, as they're termed, only exist at the time points when the clock ticks. So for the first clock, it ticks every 0.3 seconds, and the variable semantically does not exist apart from every 0.3 seconds. If you want to use it in the continuous time series, for example, you use the hold operator, as it's termed in the literature, where you hold that variable constant for the duration between clock ticks. And so if you, with the current implementation in the library, if you ask for just UD1, it'll error out if it's not at the same time series. But if you ask for hold of UD1, it can recognize that that is a continuous variable and it can access that at the continuous time series. And as for interpolation, that's actually something we're planning. So interpolation right now is implemented in SciML base. And one thing I really want to do is try and get it down to symbolic indexing interface. So again, we have one implementation for interpolation, and moreover, we can do the similar sorts of cached interpolation object for a particular symbol. So there are workflows where you want to interpolate multiple times with the same variables, and you pay the index lookup cost multiple times, which we want to avoid.
Thank you.
Yeah, let's have just one more question with an eye to catch the schedule, and Ayush, just select one. Or yeah,
sure.
we'll have
Okay, yeah, please.
Okay, sorry, just with an eye to catch the schedule. So yeah. You
Okay.
can ask later. Yeah. Okay.
So is this working? Yeah. I personally have some packages which use like a very rough symbolic indexing using dictionaries and address maps and the works. Very hand optimized stuff. Is there like a roadmap or a tutorial how you can go from such primitive solutions towards a symbolic indexing interface, or are there any in the making?
There is actually pretty comprehensive documentation that we try to maintain. And it has a complete tutorial of how you might want to implement the entire interface from scratch using nothing but like custom struct. So it just creates a very contrived example of the interface where you might have some sort of example system which actually has dictionaries mapping symbols to their indexes, and all the mandatory methods, any optional methods, and every single part of the interface is all documented here.
Yeah, this seems very familiar. Okay, thank you.
Yeah. Awesome. Let's give it for Ayush. Yeah.
Thank you.
Yeah. Thank you very much.
Good spot.
Okay, Michael, now we will connect you.
Thank you.
Some others?
No, I'm good now. Thanks. Yeah, I don't want to miss.
Screen's working.
Thank you. Thank you so much.
Yep.
Seems good. Is it on?
Nee, ik zeg nou. I'll turn it on there.
Okay.
This one is on.
Yep.
So you want me to check.
Okay.
All right. So our next speaker is Michael from JuliaHub. He will be talking about JSML, which is Julia Sim Modeling Toolkit.
Modeling language.
Language, sorry. Yeah, so let's welcome Michael. Okay, so good luck.
All right. Alrighty. You guys can hear me? Ooh, it's kind of loud, actually. Okay. All right, so I will just get started. Thanks, everyone, for attending. So I'll be talking about Julia Sim modeling language, and I'll explain what that is in just a second. But I want to start by talking about what modeling toolkit is, because it really doesn't make any sense to talk about Julia Sim modeling language without really understanding what modeling toolkit is. I want to make sure everybody's sort of on the same page there. So Chris Rackakis gave a nice talk yesterday. I don't know how many people saw that, but it was a workshop, actually, and talked about these things. So I'm kind of continuing on from there, but I wanted to give a quick summary. So modeling toolkit uses a set of Julia macros to build models. And so I've just shown some examples of these macros up here. In modeling toolkit, you need this concept of a connector. So you can see that you define a connector using the @connector macro. You have this concept of a model, so you use the @mtk model to define that. There's a bunch of other macros that are used inside the macros for things like extending, which is like inheritance, defining parameters, defining equations. And then ultimately, when you compose a system-level model, you use the @components macro to bring in those components. I think it's pretty intuitive to read, especially if you have a background in these sorts of things, I guess. But basically, the idea here is that this is a RC model. You create a resistor, a capacitor, a source, a ground, which are electrical components, and then you connect them all together over here. So that's how it's done in MTK normally. That's the normal MTK syntax. So there's a couple of complications that I want to talk about here that complicated. These complications arose really in the development of Julia Sim, which is the JuliaHub product. So these aren't really complications with respect to MTK itself, but really in our efforts to bring or to surface modeling toolkit capabilities in our product and in our graphical user interface. So the first thing that actually Chris alluded to even in his workshop was the fact that there's this uneasy tension between the imperative semantics of Julia and the sort of declarative intent of these macros. So one thing to keep in mind is that ultimately modeling toolkit is going to do a bunch of symbolic manipulation, essentially algebra, on the models. And that requires a fairly limited vocabulary. You need to have a representation of your system that it can reason about and transform. And having just a Turing-complete imperative system for doing things you can't really reason about it. So we need a limited vocabulary from the start in order to do the transforms that modeling toolkit does. And in the case of the macros, you see this declarative system used to describe things, which works very well because it has a limited vocabulary. It doesn't open you up to being able to run just arbitrary Julia code in creating those systems. And these macros then provide this declarative feel in describing the behavior of components and systems. And they ultimately leverage the Julia language, which is this imperative environment. And so there's this sort of tension there, as I said, between the sort of imperative side and the declarative side. And when is it, when do you have to stay within the declarative aspects, and when can you use the imperative stuff? Yeah, and then there's a whole bunch of sort of implied semantics around those Julia macros that are not necessarily obvious if you were to just boot up VS Code in Julia mode. It doesn't know what those macros actually mean, and so it can't really enhance the functionality there above and beyond what is just Julia. So the question is, how do we reconcile these sort of imperative and declarative aspects? So another complication that comes into this is this notion of doing graphical model composition. So everything I showed you before was textual. So when we're using Julia macros, we're sort of inherently using this textual way of composing models. But what if we also want to, at the same time, compose models graphically? And by that I mean, dragging and dropping components down onto a canvas and connecting them up. And so, this is the example of the Julia Sim macro. But we also want to be able to essentially represent models in a form like this, right, which is graphical. And so this is another complication. How do we reconcile these two worlds, this textual and graphical world? Another thing that we are sort of concerned with is round tripping, and I'll explain a little bit more about what I mean by that in a second. But basically, imagine you create a model in a GUI, and then you want to, by dragging and dropping something, and then you want to then edit it as text and then go back to the GUI, for example. So if you built such a GUI, you could write Julia code. You could imagine a system that would take a diagram like the one on the right and could generate the code that you see on the right here. But then what happens when you want to actually edit it in the textual mode and then load it back into the graphical user interface, right? There's this sort of back and forth, what we call round tripping. How would you manage that? If you just have a system that takes a graphical representation and generates code, then how can we iterate on that? Because the graphical information that we need isn't really present in what you see here in this code. Things like where components are laid out, how the connections in the system are routed, and so on. So we get this complication of again mixing this imperative and declarative stuff and reading and writing these things. The fourth complication that comes up is the fact that if you're going to be creating a GUI, today you're largely going to be doing that in a browser or perhaps in Electron or in VS Code. But in a lot of these cases, you're leveraging essentially a web browser, one way or another. And so if you're in, also this applies when you're creating a VS Code extension, is that you're essentially using a web browser as your environment. So in these environments, the GUI itself is generally going to be JavaScript. I mean, you can use WASM, but I'm just sort of setting that aside for the moment. These are essentially JavaScript execution environments. And I put JavaScript/TypeScript here because a lot of the development is now actually done in TypeScript, which is a superset of JavaScript. But evaluating that MTK code, evaluating those macros, just to even figure out what constitutes your system model involves a Julia execution environment. How are we going to do that if the environment where we're developing the graphical capabilities is not a Julia environment? And so the problem that we have in this case is that we have modeling toolkit and this amazing ecosystem in Julia as sort of our starting point. And at some point we have to deal with this fact that we have the browser, VS Code, and potentially other environments that we'd have to deal with, but these are the big ones. And so we have this sort of middle layer, what I refer to as the sort of composition layer, how we actually build models. We're not actually running code, we're just talking about the construction of the models themselves, what they're composed of. And how do we do this, right? Are we going to do this in the sort of browser? Are we going to do this in Julia? And if so, how do we get these two, the top layer and the bottom layer, to really talk to each other? Do we build some HTTP API? What do we do there? So those are some of the complications that we were looking at. And so the question is, how do we address these? So in terms of model composition, it's not a question of whether we do this in Julia or in TypeScript. I think that's sort of the wrong question. Because those are still both imperative languages. We're really not dealing with this tension between the declarative aspect and the imperative part in these cases. So what I felt, in my opinion, we really needed to do was to come up with a declarative vocabulary for what we mean by describing models, and just focus on that. And so if we do that, then we have a system that we can sort of reason about these models, these compositional systems. It's not a Turing machine, right? This is just essentially a formal representation of what we mean by a model, what it means to connect something, how we define the parameters and physical types of things. That's our vocabulary. And so the solution that I came up with here is this JuliaCon modeling language, for better or for worse. So in the JuliaCon modeling language, we have this declarative domain-specific language, right? So it's neither TypeScript nor Julia. It's just a very limited language for describing the composition of models and the rules about composing models. So you can describe the model behavior, the fundamental equations that are in these models, but you can also describe the composition. So if you want to build a circuit model, the idea that you bring in a resistor, you bring in a capacitor, you connect those up. So that's not a equation or math-based sort of composition. That's just relationships between entities. from my perspective, the nice thing about it is that it runs natively in a browser. The actual language kernel that implements all the semantics and the parsing is all done in TypeScript. It allows for a bunch of strong static checks to be done on these models that you're composing. Because it's running in the browser and it's integrated into the graphical user interface that's developed, you can get immediate feedback on things. If you try and connect two things that shouldn't be connected, you get immediate feedback on that. It doesn't have to make some HTTP request and then come back with an error to tell you, oh, that wasn't allowed. It can make those decisions immediately, and in fact, generally synchronously in the browser, so it's really immediate. And this being integrated into the browser allows us to create this fast reactive user interface. So the thing is, though, that there's no imperative semantics involved here. So there's no functions. All that stuff comes from Julia. So the scope of what I'm talking about here is very limited. It's just about describing the composition of the models. Anything that involves actually running anything imperative, loops and ifs, well, not quite ifs, but non-ternary operator kinds of if things. That's all done in Julia. So GSML, the closest analogy I can describe here is that GSML is like HTML or XML or something. It's just trying to capture the representation of a very specific domain. So here are some examples. So you have the MTK macros on the left. You have the GSML code on the right. So one of the things I'll point out is that we have the notion of physical types in GSML. So there's a volume type, and it includes the units of volumes. So actually, this should be voltage. I just realized that's a typo. It should be voltage. My apologies. But and then you can do things like you can define a connector which has a voltage and a current. You can do the same sorts of things that you do in modeling toolkits macros, which is to extend from an existing base class and then add additional equations. And similarly, when you compose systems, you do it in a similar way. You can see sort of side by side, describing the same system in both. So you might think, okay, well, this is just an alternative syntax. What's the benefit of this really over the MTK macros? Well, the one is that we can do it in a browser, and that so we don't have to have a Julia environment running. Another is that we can add graphical information to this, and so I'll show some examples of where this comes in. Actually, I skipped one slide. One slide I wanted to point out is that when we generate Julia code, we actually generate the MTK code from these GSML component models. So ultimately, it all ends up being in Julia. This is an important point. But we can also walk through the definition of that component, like this resistor, and extract out a bunch of useful information, and then automatically generate the doc strings for the functions. And this that shows up when you just do a help in the Julia REPL on that component. You get to see all this information. What is R? What's its default value? What are its units? What connectors does this have? What internal variables does this component have? Which is relevant for, like, Ayush gave a talk before me about the symbolic indexing. And that's actually referring to these sorts of things, the VNI values that are inside of those. So that's one thing we do, is we generate the doc strings. But we also have this concept of metadata that we bind to these definitions. And normally, if you're looking at this in a graphical user interface, you won't even see this metadata. This is the textual representation. But when you're doing graphical composition, we don't see this. And when you're editing these things in VS Code, they can be folded up, so you don't see them. So I just want to make it clear that this might seem noisy, but the point is it's not in your face all the time. But I just want to point out that it exists. So this is an example with a connector pin here that we can define the appearance of one of these connectors on a resistor or a capacitor. And so we use metadata to do that. So within this connector definition, we have this metadata, and we have a schema that defines what's legal metadata, exactly what form it should take, and we can validate that the metadata is legal and everything. So this allows us to define the icons that will be used. It allows us to define some of the attributes that are used when we stroke connections, for example, so that we can say that when we stroke the connections, that they should be a certain color. And so anyway, so that's the metadata field in the components. Another aspect of metadata is if we were building, for example, a circuit model, and you can see that over here. There's a couple of different things we can do. One is We can specify the placement of these things, so the metadata attached to this allows us to say that this particular component, this resistor, should appear here in the diagram. It should be rotated in this way, the exact extent of it, so we can make it larger, smaller, things like that. That's all in there. And then we can also include metadata that includes the routing between the connectors. So there's a connect statement back here that connects these three things. But what the metadata is doing is it's allowing us to specify how that's routed, including things like junctions within the routing. So I won't go into exactly what this metadata means, but it allows us to handle these sorts of complex routing descriptions. And with this information, we can then just render the graphics for this component. We can generate a graphical representation. Another thing that we can do, though, with metadata, in addition to just graphical stuff, is that we can include other information. So, for example, we have this sort of reserved this JuliaSim namespace in metadata for stuff that is specific to our tool, but you can create other namespaces. So, for example, Gary at Boeing wants to put metadata into his component. He can add that metadata under a separate namespace called Boeing, and then he has free reign over that stuff. So he can put part numbers in there. He can put processes or gateways or whatever information he wants to put in there. He can put in there, and it's preserved. In this case, this is another example of generating a test case, right? So we've specified some metadata in here that describes a particular test case called case 1, the stop time for it, expected outcomes, expected values for that test case. And what this actually does right now with the JSML compiler is it generates essentially the runtest.jl file, runs the simulations so that, and then compares the results at that time. So what that means is that you can just go in and run test on your package, and this declarative chunk of metadata gets turned into an actual imperative test case that gets generated. Okay, and so the result is that you get stuff like this. This is an actual screenshot of JuliaSim GUI, and I see some of the developers of the JuliaSim GUI in the audience. Anyway, the net result of all of that metadata is that we can then render these sorts of things. We can generate the information that you see on the sidebar, right, about what components are defined within a given package. So this is JuliaSim. So it reads and writes JSML. It allows you to do drag and drop model composition. Each component library is just a normal Julia package. The way that this works is that the JSML representation is used to generate Julia code, and that's then just a Julia package, which you can package up, put into a registry. You can add it as a dependency, import it into your system. So it leverages the Julia package manager to manage all the dependencies, and it uses JSML metadata to handle the layout and the routes and things like that. You can see, for example, a junction is rendered here. Then we have JuliaSim Studio, which is an extension for VS Code, which is another way to interact with this. Because the language kernel is written in TypeScript, it not only runs in the browser, in the previous example I showed you in JuliaSim, but it runs very nicely in VS Code. So I have a quick, I'll show a video in a minute, but this adds syntax highlighting. It integrates in the JSML compiler for doing the static analysis and the code generation right in VS Code. Each component library is just, as I said, a normal Julia package. So it works with the Julia extension, with the Julia Hub extension, you can do things like metadata folding, which I alluded to earlier. And then it also still supports being able to render a model. So you can still look at the graphical representation even when you're in VS Code. So here's just a quick video that's going to walk through this. And I'll try and make this full screen. If I can figure out how there used to be a button to do this, and now I don't see it. Shoot. Okay, well, anyway, I would just be a little bigger in that case. But you see that the metadata is folded there. I open up a Julia REPL. I can see that there's a problem with the types here. I get the immediate feedback. There's a problem there. I can go through and show you the resistor model and the 2-pin model, just looking at the code and how it's syntax highlighted. If I bring up the Julia REPL, I can show that if I type the name of a model, it actually renders the model for you right there in the VS Code, and I can perform this test that you see here. So it'll go off. It'll run the tests that I defined that I talked about before, which are going to compare. They're going to basically check for regressions. They're going to make sure that the models there's a sort of test specification for those models. and it's going to check to make sure that the initial conditions are what we expect and that the final conditions are what we expect. And in the future, I want to add the ability to actually look at the trajectories themselves and actually make sure that the trajectories are within some tolerance of an expected result. So anyway, this will run through and it'll say, oh, you passed all your tests here. I don't know. I guess I won't bother waiting for that. And so in terms of future work, there's a lot more static checks that we could be doing. I showed one example really quickly in that VS Code thing, but it went by very fast, where if you were to define, if you were to try and use a component that didn't exist, if you tried to use resistor 2 as your resistor and there is no resistor 2 anywhere in the set of dependencies that it has, then it'll immediately flag that as an error, right? And this is the difference between the MTK macros and something like this, because in MTK, it would find that error, but only at runtime, actually, when you try to instantiate the system, whereas we can get immediate feedback in the VS Code extension that no such thing exists. There's a lot of these kinds of static checks that we can do, and I think ultimately, for an engineer, I mean, my background is in engineering. For an engineer trying to work with these systems, I think the more that we can front-load a lot of these things, the better it'll be in terms of their experience, giving them very specific feedback on what's wrong with their systems. Also, we're working on expanding the set of standard library components that are available. So we're working on an electrical component library, mechanical component library, hydraulic, thermal, and then control systems. And then ultimately, we've been doing a lot of interesting work with state machines. We want to be able to integrate that into the language as well. So, yeah, there's a lot of cool stuff I think that we can do. This is really, I mean, this is the first public talk even on JSML. I mean, it's really, very fresh. And I think there's a lot we can do there. So a couple of conclusions. I mean, we have this declarative representation for model behavior and model composition. We can translate this directly into Julia code using MTK. The language semantics can be run natively in the browser for immediate feedback. And of course, elsewhere, we have a command line compiler. We have a VS Code extension. It's a single representation that allows us to support quite nicely both the text and the graphics and to actually go back and forth between them. So, there's no compromise here in the sense that if you want to be doing stuff in Git or want to be doing things in CI in a sort of headless mode, you can do that. Or if you want to be using a graphical user interface to compose models, you can do that. We don't have to make this sort of false choice between having a nice GUI desktop tool and having something that can be automated in CI. We get both of these. It's readable and writable by both humans and machines. And it has this limited vocabulary by design that constrains the expressiveness so that we can actually reason about things, and delegates, as I said before, all the imperative stuff over to Julia. So it's still very much leveraging Julia and built on top of Julia. All the functional pieces come from there. And that's my talk.
Okay. Well, there's a sea of questions, so I don't know. Yeah, somewhere there. Let's go. Yeah.
I have not tried it with Pluto.
Yeah,
that would be a question for
yeah,
Penny.
Please speak to the microphone. Yeah.
Will this also work with Pluto?
I can answer that. The answer is no right now, but since this works totally in the browser, it's something that we can integrate.
Yeah, I'm afraid. Yeah, you need to speak to the microphone. Otherwise,
yeah.
It will
Okay.
be,
I'll speak for Penyatis. So I guess. So yeah. So he's actually one of the developers of the Julia Sim GUI, and he's also one of the contributors to Pluto. So he says eventually, yes, we're in good shape there, but not yet. I think I captured his sentiments there. Okay.
Thank you very much for your nice talk. One question. Are there plans to implement arrays of elements?
I have some ideas on how to implement arrays, and there's already array support in MTK. It's just a question of time. I mean, there's a lot of fronts on which to try and expand the capabilities. That's definitely one of them. It's a challenge when you try and do arrays and combine it with the graphical user interface. And so we have to really give some thought as to exactly how we want to express that both graphically. Textually, it's pretty straightforward, I think, but graphically, it's a bit of a challenge.
Thank you.
Yeah, perhaps somewhere there.
Somebody pick somebody.
Yeah, thank you. So this reminds a little on the Modelica annotation system. So I'm pretty sure that there are some improvements compared to Modelica, but are there any? Did you try to make some things better compared to the quite old Modelica?
Yeah, so in fact, I will say that at the American Modelica conference, I've submitted a paper which will hopefully be accepted that addresses exactly that point, which is to say that Modelica is a very widely used technology, but I was around when it was developed. It was developed 30 years ago, and so there are a lot of things that changed in the technological landscape, which is no fault of Modelica. I mean, time passes, things change, technologies change, and so yes, I think there are opportunities that JSML can take advantage of. And what I tried to do in this case was, being pretty knowledgeable about Modelica as well, was to try and take what really worked well in Modelica and incorporate that. So you spotted that with the annotations. Although those are JSON annotations, I should point out this is an example, right? JSON is now ubiquitous. Everybody can read and write JSON. Modelica has its own structured data syntax. There's just no reason to have that now. So we just switched to JSON. We use SVG for graphics because there's no reason to use something other than that. So those are examples of how we tried to modernize some of those concepts.
Yeah, thank you very much.
Yeah, we'll have just one more question there, and for the rest, just catch Michael after the presentation. Sorry. Yeah.
Hi, thank you for the presentation. Do you also have support for discrete events?
Well, I mentioned the state machine stuff in there, so that's one aspect, and that's another example where I think we can actually move beyond the capabilities that are in Modelica. We have a vision for actually having primitives in the language for state machines specifically, as opposed to component libraries that do state machines but are a little awkward to use. So yeah, we have a plan for actually integrated capabilities for state machines. So when you describe the behavior of, for example, a clutch, and the sticking and slipping modes of a clutch, that you could actually represent that as a state machine instead of a bunch of discrete variables that you kind of knit together with when clauses into a state machine. You could actually represent directly in a state machine. So again, that's one of the many fronts, along with array components, that we want to get to, and we have, I think, pretty specific ideas about it. It's just a question of bandwidth and demands. But yeah, I certainly hope so.
Okay, let's give it up for Michael again. Yeah, great. There are two speakers for the next session. There's Bradley and Venkatesh. Okay, so you'll be giving the updates on standard library of modeling toolkit, right? Okay, great. So there's a connector. You want some water?
No. Let me mic you up.
Show yellow card 5 minutes before the end of the presentation. Okay.
It's working. I'll open your mic in a second.
Yeah. Hi, I'm Venkatesh Bhatt. I work as software engineer at Julia Hub. Me and along with Brad Carman, who is director of consulting services at Julia Hub, we are here to present a talk about all the updates that native DSL of Modeling Toolkit has, just after Mike told everything that it lagged in, why we have JSML, and also give update on standard library, the conventions it has adopted, and etc. Brad has a lunch and learn right after this, so I'll be presenting it completely by myself. You should all attend the lunch and learn after this. So Modeling Toolkit standard library is sort of, it has fundamental components already written out. So you can just use those to build out the composite systems. It has mechanical, magnetic, thermal, and electrical components, which are based off similar to Modelica standard library. It has all these components written out. So recently we have updated what are the conventions that we are following in our connectors. So generally for every domain there is a connector. You have a through variable and an across variable. Through variable is, it should be a time derivative of some sort of conserved quantity, and the conserved quantity itself should be expressed by an across variable, so that you have an energy dissipation equation and a flow equation. For electrical domain, this would be voltage would be the across variable and current would be the flow variable. It gives out one equation at the end if you build out the system with a resistor and a capacitor and a ground. And that's why our electrical domain will have voltage and current in its connector. In the translational domain, we have departed from Modelica standard library. Instead of a position and a force, we are using a velocity and a force. Here, if you write out similarly for the damper and mass and a fixed as a ground, then you would get a single equation that you have to solve, which links the force and the velocity. So we get both the we get to solve that. We also have translational position domain. If in case you do still want to use similar to, whatever is similar to Modelica, then we have equation for position and force. And if you write out similar model for figuring out what equations it's solving one that connects position and velocity, and one more the energy dissipation equation. So the comparison between these, the numerical difference between the velocity that you would generate with these two connectors is very negligible. So at the end of the day, based on what your model requires, if it already requires a position variable, and if your model needs that, you can just go with translational position, or you could stick with translational. One more difference would be that translational connector, you would need to initialize less number of starting variables, because there are less number of variables there. And then the another thing that we added was sign convention. We swapped out a little bit there. The idea is whenever there is an input component like a constant force, and you connect it to a conserved component like mass or capacitance, then the direction, the positive value of flow, whenever it is flowing out, then the accumulation of the conserved quantity should increase. So if you see in the equation, flange has a negative force. That is, force is now flowing out of the constant force. And then when you connect it to mass, it is increasing the velocity, the conserved quantity of that mass as time progresses. So now entering, so these were the conventions that we wanted to update you on. And then now updating about the second part of this talk is about all the updates that we have done for the native DSL of modeling toolkit. MTK model already supported parameters, variables, components, and equation blocks, but it was limited in its capacity, and it couldn't do things like arrays, or it couldn't really have looping statements, and etc. Along with those, we have added new blocks for specifying defaults and guesses. This is similar to just passing defaults and guesses to the ODE system. You can have variable and value pairs listed out, and that gets passed to the ODE system while it is building. Currently, you can't specify it as a keyword, so whatever you are specifying here will be the override. So if a user is giving input values for these, those will not be accepted, and only the final, whatever is hard-coded, will be passed. This will change soon, where default and guesses can also be a keyword, and you can pass those as dictionaries to the component. Along with this, there was one issue that arguments could not always had to be symbolic in nature, but sometimes when you want to specify, say, length of an array, or you want to set Boolean flags and etc., that would be a problem. So we have introduced something called structural parameters. These are not added to the ODE system, but these are used to influence the structure of the component itself, what you want to add and what you don't want to add for those kind of things. I would like to start building mass component and side by side just to showcase what we are using, so update is seen. So now MTK model also supports conditional statements. If you want to have a gravity component element for your mass, then based on that, you can add the parameter g and also influence the equation, how it is written out. here, one thing to note is you cannot have symbolic parameters as the condition, because these are executed while defining the OD system itself. So these have to be a structural parameter. That's why that whole keyword was introduced. If it makes sense to club all these together, you can also club within an equation within a condition itself. We also want to specify position of the mass. So whenever based on the position condition, you add position variable and also an equation that links it with the velocity of the mass. So to take it forward, for the next step, I would like to build out a composite model of a train and stopper system. The QR code has the relevant docs where you can read out the whole model and optimization of that and such. So here, the idea is we connect train cars with couplers, and you have a stopper. Whenever there is a contact between the train and the stopper, train comes to a halt after some point. So whenever you're building out a composite model, you would have some repeating element in it. So you can have partial blocks defined out. Here, two flanges, which has, as the name suggests, it has two flanges. If you have equations, components, just like any other MTK model, you define them all, and then you extend that in whichever model you want to extend it in. Here, one thing to note is, if you have arguments that you want to pass, then you have to specify while extending that component. Anything that is defined while extending, that is added directly as an argument of the MTK model, of the base model that is of train car. So flange A and flange B.V, both will be added as an argument. You don't have to dot access it as two flanges dot flange A or whatever. That's a departure from how the components are, variables inside a component, subcomponents are accessed and versus of a base system. Let us add a mass component to the train car. Here we are also declaring where the position A and B, that is starting and ending point of that train car, would be. And we connect out a flange A and B, which is for connecting to other components of the train. So train car coupler is a composite model of spring and damper. Instead of building them out from scratch, I'm using from the mechanical translational library. I'm adding a spring constant, a damping coefficient, and a starting velocity of the coupler. These can be set by user as it is declared in the parameters. These are also added as an argument, so user can just pass it. I am defining a subcomponent spring and a damper, and also specifying how these spring and damper connect with each other. And if you build out the train car coupler model and you expand all the connections, and if you see the full connections, it gives out how these spring and damper equations are connected, and everything is just added. The whole acausal modeling's advantage shows out, and we don't have to write the entire model from scratch. Moving on to the building train. Even train, we do specify a initial velocity, and then we specify a spring constant to it and a damping coefficient, and we define bunch of subcomponents for train car and coupler, and we give out a mass of suitable range, and then positions are defined according to where it should come in the train, something that makes sense. And then you go on connecting cars with couplers one by one, so that it is all connected and the train equations get built out. And if you plot out the displacement of this, you can see that there is a constant velocity. They all line up, and the model actually instantiates correctly. For defining a stopper, the stopper would have to exert that amount of force. Again, stopper also has two flanges and two velocities for both the starting point and a force which is defined according to that equation. I define out how the connectors are equated to these velocities, and how differentials are also connected, equations for that. And when you build out the whole system, the train has an initial velocity. Stopper, I give out a very small spring coefficient and a really high damping coefficient. So stopper brings train to halt quickly. And if you notice, the starting position of stopper is right there where the contact happens for the train. And I ground it with a fixed reference. So we have also introduced a new macro called MTK build. So it basically builds out a system and also structurally simplifies and gives out the equations, the final equations. You can also pass some of the keyword arguments like fully determined, etc., and values to the subcomponent variables as well. MTK model now also supports events. You can define continuous events and discrete events as pairs of equations. To show it in action, if you have a unit mass and friction, I'm declaring that when velocity is 0, there is you have to treat that as a continuous event. And when you build out the model and solve it, the whole thing just works. Yeah. Thank you.
Great. We have quite some time for questions. Any questions? Right. Yeah. Got you.
Yeah. You had the train car model with like the multiple wagons, the multiple cars. Can you now write this in a for loop to have n cars instead of 4?
Yeah, actually, it can be written out. I don't think components support. Components should support the for loop as well. So you have to individually write out the for loop for the components and separately for the equations. You can't define both together, though.
Okay, so then it would be like components 1 to n.
Yeah, so 1 to 4, you write out a for loop inside the components block to define out how they are, the values according to that should be defined once, and how they're connected will be a separate for loop inside the equation block.
Neat, thank you.
And there's also a composite.
There is a comment from Chris, so can you just speak to the microphone? Yeah, sorry.
Yeah, and there's also, you can use Julia comprehensions as well. So comprehensions are a nice way to kind of do array-like things as well. And there's a comprehension syntax that is also supported inside of there.
Thanks very much for the talk. Where I work, I do a lot of things that is continuous and discrete. For example, the embedded software in a computer is discrete. And sometimes you have to run a real complex algorithm and so on. It's just one by one representation of the embedded software. How far, or is it already possible to use MTK to simulate these things, like using callback? And if something triggers inside this callback, it changes the dynamics. Is it possible to do this?
Yeah, there are discrete and continuous callbacks that you can define. You can either specify them within the continuous events or discrete events, and if you are writing out as just Julia function, even then you can pass that as a pair of equations for what conditions should be met and what should be the effect because of that to the ODE system while building out.
Yeah, and I do want to mention a few things here. So one thing to mention is that Frederick will be giving a talk on hybrid systems, and he'll go into a bit more detail on the current state of modeling toolkit for hybrid systems. And so please check that one out. I mean, he comes from a robotics background. Actually, came from cognibotics before, right? So his big thing has been how do we make it so that way complete control circuits can work with this, right? So there's that going on. There's the state machine integration, right? So modeling toolkit support of full state machines as part of its compilation process. And then there's a lot of other things that are required. So I would say that we're not all the way there with hybrid systems yet. In fact, one of the things that we really need to make sure that we're doing is, for example, composition of event systems. So for example, if you have multiple discrete events, it lowers it to multiple discrete callbacks right now, right? If you kind of know the differential equation syntax, right? But what we should be doing within the compiler, for example, is we should be combining them into one discrete callback that is the understanding, you cannot have this, and this happen at the same time, so we can compose these checks and lower it to much more efficient code. Some of these more efficient compilation processes have not been done yet on hybrid systems, but this is a very big topic within Julia Hub right now, and so we are going to be doing a lot of work on the modeling toolkit compiler with that. Another aspect as well is the connection between structural simplification and hybrid systems, right? Because, for example, if there's a variable that you only have within a event, you don't want your DAE simplifier to delete that variable because it realizes there's no equations on it. We need to do a few things within the events, within the simplification engine to be able to better support those kinds of use cases. So there's a lot going on with hybrid systems. There's a lot that's working well. There's still some things we need to do in the compiler, and it's one of our main priorities over the next year. Thank you very much.
Are there more questions?
This is more of a also reply to that, which is specifically for changing equations within callbacks. One very well-tested way that works for doing that is you can introduce a parameter that's either like true or false, and then have an if-else that has both sets of the dynamics. And so that way you can have both parts of the dynamics in the system, and then they'll be changed by the callback. And one of the really nice things about doing it this way is that your model is continuous, so the ODE solver doesn't see the fact that at a certain point everything suddenly changes, and that will happen outside of the solver loop in the callback purely, and so you maintain your continuity and higher derivative smoothness that you want for your solvers.
More questions? Yep. Or comments?
Since we discussed a lot of these different pieces, Chris, maybe do you want to just mention how can one get to all these pieces and download them and try them out?
Yeah, so everything to do with modeling toolkit, standard library, and such. You can find all these with if you go into the modeling toolkit standard library documentation, right? So you go to the SciML docs and you'll find that there's a whole section that is just about the modeling tools, and you can find all that. But there's also a lot of these extra compilers, a lot of these extra component libraries and such. So if you search on JuliaSim, you'll find the JuliaSim documentation, and this gives you the whole world of extended standard libraries, extended component libraries, and then also the extra compilers like the JuliaSim compiler, which is where a lot of things like these state machines live as well. So there's a huge ecosystem that's growing, and definitely because of the way that it's growing in so many different ways, we plan to be working on the websites to make sure it's much more easy to discover everything that's going on. But yeah, so there's just so many contributors and so much work going on that we will be working a lot more on that discoverability in the near future as well.
All right, unless there are more questions, I suggest we wrap it up. Let's thank our speaker again. Yeah. Thank you. Yeah, the session is over. We can all go to lunch now. Frank.
See you after lunch.
Yeah, see you after lunch. I'm not sure I'm moderating here though. There
Oh.
might be another moderator. Are you staying in this room?
Yeah.
Okay, yeah, no, probably it's going to be someone else.
Over here?
But then tomorrow. Are you working tomorrow as well?
No.
And Friday?
I'm not. No. Yeah. Well, I am working, but not here.
Not here. And then it was a pleasure to meet you.
All right. Take care. No, that's no problem. That's no problem.
There's already a functionality in JSML. I didn't talk about it, but this idea that, okay, let's say I define, let's say, just to keep a simple example, I think it's analogous to your case. Let's imagine that you have a system where you have a controller and you have a plant model, for example. And the plant model, you might have a very detailed one that that looks at like flexible bodies and things like that, or you might have a simple one that's just like, oh, mass or something. And the point is that when you're analyzing the model, you might want to actually say, okay, I want to substitute one for the other. And so there's a common interface around this, which is like I have a flange here, and I have a thermal port here, and I have another flange here, and that's what defines the interface of that thing. But the internal details, the implementation can be separate. So that's already a functionality.
This place is great. It has sparkling water for the speakers. You usually only get the non-sparkling one. Should probably add that. All right, and let me know when I'm good to go. I don't know if the stream like has to start up or something right at 2. Oh, this is gonna be pretty loud. Okay. Yeah. So tell me when I'm supposed to go. Oh, I'm good. All right, I'm gonna take all my time. All right, come on in and hear about the state of SciML. So, this is going to be a retrospective and a roadmap for the SciML organization, right? So, what is the SciML organization? It's this huge organization with tons and tons of Julia packages, and I'm Chris, and I've been working on this for almost 10 years at this point. And so what I really want to do is I want to walk through a lot of what we have done, what we are doing, and where we are going, right? So that way everyone kind of has a good view on what are all the things that are going on in the organization. And dense slide number 1, right? Because when I want to say all the things that we're doing in this organization, I think that we're talking about a bigger organization than most people think. Because most people, when I talk to you, you only talk about one part of this organization, right? Because the SciML organization, it is something with over 100 GitHub repositories, of which many of these repositories, for example, optimization.jl has like 15 packages inside of that one GitHub repository itself. So we're talking about a good hundreds of packages, and we're actually ready to register about 20 more on ODE. So there's a lot there. It's over 20,000 GitHub stars across a set of packages. I looked at the last few months to be able to kind of figure out like how many people actually show up, and we have about 100 unique contributors every month, right? So that is, 100 unique people will show up to give us a code change every single month. That's three unique people a day, right? And there's over 20 core maintainers, these are the folks that have the designation of I will ping them when I say, oh, I'm busy, please help me on this given package, right? So there's 20 maintainers spread around many packages. Most of those core maintainers have 3 or 4 packages that they take a hold of. There's a few of us that kind of do 10, and then there's only one crazy enough person to try to look at a few hundred of them. And then there's about 5 to 10 summer students and trainees that we've had every year. We started working with Google Summer of Code all the way back in 2016. And then many of those folks that we had, so 5 to 10 students per year. So we've had, I think and we've also many years we've had 15 to 20 in different forms. So we've had over 100 students that have been trained up. They become PhD students at the MIT Julia Lab. They become employees at Pumas AI and Julia Hub. And so there's this whole kind of organization of folks that we've developed in terms of people who are maintaining packages, people are contributing, and then people who we've taught everything to, and then they grow up to then have their own research labs now, right? Because again, we're talking about an organization that's now been here for 8 years, and so people who started working on it as a PhD student, they're now actually professors, and they're hiring PhD students who then help maintain some of these packages, right? So I, Chris Rakakis, am the BDFL, which means that I have, I'm the one person who decides that it's a sane thing to do to be a maintainer on this whole thing. and try to make it look as one unifying force. But what that means is that it's going to be very hard to summarize everything here in 30 minutes. In fact, I got through summarizing about 1/4 of the content and 1/4 of the repos, and I realized I had more than half an hour of content. So everyone will be disappointed because I will leave off some topic that you care about. So, you know, if you're like, oh, I wanted to hear about the state of quasi-Monte Carlo.jl, or, you know what's not even going to be in the SciML talk? Physics-informed neural networks will actually miss this talk, right? There's way too much in here. So I hope that we're going to have like a reoccurring series where we'll have, you know, more one-on-ones to talking about what's going on in different parts of the organization. Because, again, this organization at this point is huge, and there's a whole lot of people, and that means that there's a whole lot to talk about. And so what I'll say, at the very beginning, especially if you're there on YouTube, you know, if you want to connect with us, if you want to talk with us, if you want to ask any questions, go to some of our chat channels, right? We have, you know, on Slack, I think the chat channel has 1,500 people. Go ask your questions there. I might still be the one to answer in anyways. You know, go on LinkedIn, or go to our repositories and just, you know, ask questions through issues. We take all sorts of issues. Even if your issue is not even a bug report, we're happy to respond to you and say, this is not a bug report, so we'll close it, but I'll still chat with you, right? So feel free to get in touch with us in any way, shape, or form that you want to talk about what's going on here. So first question is, what is the SciML open source organization, right? And so there's one way to talk about it where you just say, okay, what's all the stuff that we have, right? And at this point, again, it's hundreds of Julia packages. And so one way to talk about it is to say, well, we have hundreds of packages, and there's things that include modeling tools, there's numerical solvers, there's analysis tools, there's tools for machine learning, and there's developer tools, right? You can almost think about it as if you took SciPy, you know, and then you said, well, I also want all of MATLAB, and I also want all of JAX, and I also want, well, everything that, you know, if you've heard of Modelica and Simulink, let's just take all of this and make sure that it all works as one giant system. If you wanted all of that at once, that's kind of SciML at this point, right? And so that is a huge footprint as to what we are, but that is what we're aiming to do, right? All the stuff that you do with numerical modeling and simulation, how do we make it so that way it's all one very cohesive, you know, piece that works all together? And so, you know, trying to picture it, what is the organization? I stole a picture from one of the postdocs at MIT and one of the students at MIT, where they created this graph of SciML where they tried to say, this is about what it is. Again, this has about 30 packages up there, so that's only 1/3 of the things there. And even there, you can start to see that, you know, but there are some major themes, right? So there are things like there are numerical equation solving packages, and there's a lot of tools for simulation, which are numerical equation solving on differential equations. There's tools for optimization, analysis, tools for modeling, right? So there are these giant kind of hubs of, you know, these core things that we're trying to do, and then there's a lot of small packages that are trying to do, you know, very specific numerical algorithms. And what we want to do is we want to make it look like this entire thing acts as one whole piece. And what I mean by act as one whole piece, what I mean is that if you understand how to use the ODE solver, because you say, oh, you know, when you use the ODE solver, you say abs_tol for the absolute tolerance, then when someone writes a thing over here where they say, okay, in SciML expectations for uncertainty quantification, I want to have an absolute tolerance, that better be the exact same keyword argument, and we should actually use the same piece of code to be able to validate that our keyword arguments are doing the same thing, so our error messages should look the same, and everything across this organization, when you do ordinary differential equations or linear solvers or quasi-Monte Carlo simulations, or, you know, all of those should have exactly the same arguments, the same argument orders, and we should make sure that everything works as a cohesive system so that we can compose it every way you want. And that's the SciML organization. And so the first timeline slide of many is, you know, here's a simplified timeline of the SciML organization. And it kind of follows my own timeline of myself over the last 10 years, right? So the first versions of everything that we're having in differential equations.jl, it actually started as MATLAB plus C code that was written to target Xeon Phi accelerators. So we have a very long history of we want to use we want to do parallel computation, whatever the fastest device is out there, even if it's a weird device, right? This got formed into JuliaDiffEq and differentialequations.jl, and so a lot of the timeline of the SIMO organization was around numerical differential equation solvers. And I think a lot of people who knew us in our earlier stages, you know us as like, this is the differentialequations.jl guys, right? But you know, that kind of grew over time. So by about 2019, I took up a position at MIT in the Julia lab, and that was kind of a transition point for the SciML organization, because that was this point where we could start getting our own grant funding, where we start to write a whole bunch of grants and be able to say, now we get a whole lab of folks. It's not just a few folks unfunded, but now it's 20 students at MIT. What can we do with this power? And we really expanded the domain from saying we solve differential equations to we do numerical modeling and simulation with machine learning embedded. And that's a huge jump, right? to go from saying we do Julia differential equation solvers, JuliaDiffEq, we rename ourselves in 2020 to say we now do this entire domain of everything that you want to do with modeling, machine learning integrated with modeling and simulation means, we should take on differential equation solvers, but we should also do nonlinear solvers, linear solvers, numerical optimization, And so we had this huge expansion that happened around that 2020 timeframe. And we've also had an expansion, a large number of folks that work with us and the maintainer groups and then the groups involved. And so that was really kind of this inflection point. And that's when we renamed to SciML, right? And we've been SciML ever since. Well, that means that in 2020, after this inflection point, we really had the goal over the next few years was, well, we need to get other solvers to that level that differential equations is at. And what do I mean by that? Well, things like linear solvers, things like nonlinear solvers, integrals such as, like all these other pieces where you say, these are other types of mathematical models, those need to get to the level of differential equations.jl as well if we want to cover all these domains. And so from the 2020 to 2023 timeframe, we had to start up all these new packages to really hit to that level. And I'll go into more detail about that phase, because we're kind of now getting beyond that phase to the next phase of integrating then symbolic tools and everything that's going on with symbolic numerics and modeling toolkit as this kind of next stage of the organization. So that's like a very simplified timeline of, one day we were just numerical differential equations, then we're everything numerical solving, and then numerical solving with symbolics. But it's been a very long journey to be getting there, right? And then where are we going next? Well, we're just continuing to grow as not just in terms of the code that we're writing, but also an organization, right? So we've launched this year the SciML Small Grants Program. So we have folks all around the world who are participating in signing up to be able to take small parts of the project, and they get bounties for what they're working on. And we can use this to be able to incentivize and grow and get more new maintainers. And then we also have a lot of things that we're rolling out in terms of targeting static compilation and really making sure we can work with embedded devices, right? Again, we started very early on as, we work on new algorithms, new math, and get new solvers. But at this point now we're saying, we're growing the organization, getting a lot of new people involved, but we're also working a lot towards getting embedded devices, getting into the work that's required to be able to put the code that we have onto airplanes, cars, and all these industrial devices. And one of the big things that's really shifting as well is that there's a lot more going on in terms of the partial differential equation framework, which I'm not going to discuss within this talk, which I know a lot of people are going to ask about. But there's a lot of things in this 2025, 2026 timeframe about more integrations between the things going on in SciML and a lot of finite element tools and a lot of the tools for finite volume and all of that, and there's things I won't even mention as well, like WebAssembly. But that's like, in a nutshell, this is the timeline of the SciML. And so I'm going to go case by case into different domains and really highlight what this timeline looks like in very specific spots. Before I do that, I want to establish a ground on which we can kind of talk about all these places with the maturity level, right? And so we kind of think about our libraries as different, there's, with hundreds of repos, you kind of have to say they're not all at the same maturity level. There's high maturity, which means these are battle hardened, and we know a lot of industrial users using it already. For example, differential equations.jl. most things that you look at and you run into with differential equations.jl, there's been 100 other people who have already looked at that, and then there's already a test case about that, et cetera, et cetera. So if most cases when someone runs into an issue with differential equations.jl, I can just ask the question of, are you sure your model's okay? And they'll come back the next day and they say, yeah, the solver was right, my model was wrong, right? Like that's, but not everything in the organization is at our differential equation solvers of maturity, right? You have some things with medium maturity, which is that they have this feature completeness, but they have not necessarily hit the level of having the full testing across a huge code base and then integrated with hundreds of other packages. There are some that are in the low maturity level, which is that they're still heavily in development. Now, everything that is there is tested and tried to be maintained as well as possible, but its feature set might be not as good, right? Might not be as complete. And then there's the research libraries, which again, we have a lot of research that's going on with a lot of new algorithms from the MIT side. And so those are kind of sectioned off, but they're still interacting with everything SciML because a lot of the research and new methods that we do, we don't want to just, write a paper about, hey, here's a new method that in theory could be fast. We want to say any new method that we come up with, it should be tested on real world models to be able to say it is this much times faster than the current fastest algorithm, right? And this is why we integrate with, we don't just have the Julia code in here. We have wrappers over all the C libraries, over all the Fortran libraries and everything, because we want to be able to actually know if we say that something's fast, is it actually fast against some of these other standards, right? And so first I want to talk about our numerical solvers, right? So an incomplete list of numerical solvers that we cover are things like linear solves, nonlinear solves, differential equations, integrals, and optimization. Again, this is leaving off some other pieces like partial differential equations and a lot of other numerical tools like exponential utilities, quasi-Monte Carlo, and these libraries that are lower level utilities, right? First things first, I think a lot of people, again, our background started with differential equations. So the first timeline that we should give on, what are we doing right now and what is improving is, let's start with differential equations, right? So in 2016, that's when differential equations really started, and it really was hitting these features of, high performance, type generic, and with a robust event handling system that was kind of expansive, right? It really came out right out of the gates with saying, this is the expanded feature space that we want to support with differential equations, and this is how the next generation differential equation solver should work, right? When we came out with that in 2016, we really just had a bunch of methods for non-stiff equations and Rosenbrock methods for smaller stiff equations, right? Over the next 2 years of the organization, we then worked to build up a lot of the tooling for methods for larger scale stiff differential equations, right? And then, by 2019, we started doing things like automated sparsity support, so that way you can look at your code, automatically find what the sparsity of the Jacobian would be. By 2021, 2022, we started hitting this point of, now we're able to outperform sundials and be able to really be actually the fastest for these larger scale operations. And with the standard methods, right? So what have we been doing since we hit that benchmark in 2022? Well, we've been doing a lot of alternative methods that use alternative ways to get more performance. So one case has been these parallel extrapolation methods. So these are methods that, even though an ODE is something that's sequential, you can actually do different time steps all at the same time, and then you merge them all together. And if you do that with parallelism, you can get even more performance for ODEs up to size 200. And there's a lot of new solvers that we're developing along those lines. So that way, if you're in that range of 10,000 ODEs or less, there's a lot more performance we can get out. So that's kind of been a lot of this work since 2022 or so. And then 2023, we had, of course, the new GPU methods that were able to, they were about 1,000 times faster than our previous version of the GPU methods, and it was about 20x to 100x faster than what you see in PyTorch and JAX, because it was using a kernel generation approach instead of an array-based approach. So these last few years have been kind of going more into that area of how can we use parallelism effectively to go beyond all the differential equation solver algorithms that you see, from before. So, the first 5-6 years was what kind of optimizations should we be doing on the things that exist, and then it's new algorithms that can exploit more parallelism, because every computer that you run into has multiple cores, but most algorithms for ODs are not multi-core, right? So then what does that mean about our future? Well, in the near future, what we're doing is a lot of major performance improvements, again, on implicit methods for stiff solvers, right? This includes things like integrating nonlinear solve.jl, right? We spent a lot of time on getting these new nonlinear solvers together, integrating that into the ordinary differential equations.jl framework instead of having it have a separate nonlinear solver will mean that things like line searches and trust region methods can be used within the stiff ODE solvers. And there's a lot of performance advantages we'll get there. Also from the 2025 timeframe onwards, we have some research projects in new explicit ODE solvers. I'm not going to tell you how, but I think that we should get about 2x to 6x faster than the current explicit ODE methods that we have. And you say, oh, but explicit ODE methods that were done in the 70s. No. We have a whole way that we're going to do this differently. So, but that's been in progress for the last so many years. So, and then also making sure that we expand the package so that way all the code that we have, most of it is, we generally make sure that it's type stable and that it is non-allocating, but what we're going to be doing over the next year is making it so that way, we actually have proofs of non-allocating and proofs of static compilability, so that way we can just ensure that if you use anything within the ordinary diffie package, you know that it can statically compile for these embedded applications. Because again, that's kind of this real-world approach and this real-world kind of problem that we've really been focusing on. So we're talking a lot with groups that do things like industrial robotics, and this is really a area that we're targeting. There is something to mention, that is there are plans for an ordinary diffie v7 and that's probably only like 2-3 months away. So what would be the breaking change here? Well, the breaking change is that most algorithms that most of you don't use will not be imported by default. and that's the way to say it. I mean, because if you think what's actually happened to the differential equation solver is it's actually 10 megabytes of code, right? Like I'm not talking about like I compile it and everything. I mean, like if you look at the files for ordinary diffie Q, there are so many ODE solvers inside of there that just the files themselves are 10 megabytes. It's in the order of a few million lines, and this comes down to the fact that you have these tableaus for Runge-Kuddy-Chevy-Chev methods, and you don't need to know about all that. But literally, the size of our ordinary of the repo is about the size that a lot of people generate code to, right? Why is it like that? Well, we just have hundreds and hundreds of methods, and then most people only use 10 methods. And so what is the reason why ordinary diffie Q takes a while to load? Well, it's because we load all those methods. So we should take a lot of those methods and move them out to different modules, so that way you don't install them by default. And this is actually something that takes a lot of time. It takes a lot of time to move a few million lines of code. But we are almost done with that. And so there will be this breaking change in the near future, where if you happen to be using something like implicit Euler-Barycentric extrapolation methods, then you need to do using ordinary diffie Q implicit extrapolation. But the standard methods will still work. It just means that if you're doing one of these very specific methods for a type of PDE and you found like, oh, this thing is actually really fast for my type of problem, you will now need to load that solver, that specific solver. We're not going to load every single solver by default. So so there is a plan for a breaking change, but again, we actually don't make very many breaking changes. I'll give another talk in the near future, or almost right after this, about our development processes. Our development processes on downstream development means that if you make a breaking change, you have to go to make a PR to all downstream to every single repo that is using this piece of code to tell them how they should be updating things, and that kind of forces our developers to never want to make a breaking change, right? Because we have all these downstream tests and everything that try to ensure this, and this means that if you actually go to the tutorials that we made in 2018 on the differential equation solvers, you go to that YouTube tutorial that we made in 2018, you take that code, that tutorial still runs today. The only difference is actually that was back when Julia was in Julia 0.6. Julia was not at 1.0 yet, so there are some syntactic changes you have to do because Julia, the base library, has actually changed. But the ordinary differential equation interface is exactly the same. So this is actually going to be the first major breaking change that we've done in a while, but even then, it should only change code for people who are doing something weird. I like it when you're doing something weird, but that's how it has to be. I'm way behind on time. So, okay, simplified timeline for other core solver packages. So again, the differential equations where we started, but then a lot of what happened was we realized that, oh, hey, there's roots.jl, and for implicit methods, we use nonlinear solve.jl. But over time, we started to see that, things like nonlinear solve were not up to the SciML standards. And what do I mean by the SciML standards? Well, we start to say, well, we have, we want to be able to support every linear solver. When you work on GPU, which is auto GPU, we want to have automated stiffness detection, and we want to be able to do things like if you have a sparse matrix, if you have, you don't have to tell me what the sparsity of your problem is. We'll automatically detect the sparsity of your Jacobian on all this. And a lot of these other tools in the ecosystem did not reach all those features, right? So we started off by using things like roots.jl and nlsolve.jl, but over time we started to say, well, we want our own different linear solver interface, so linearsolve.jl. Well, we need to be able to do more things with nonlinear solvers, so we drop nlsolve and we start to have nonlinear solve.jl. And so all these kind of pieces have been built up over time, and a lot of them started in the year 2020. They took about 2-3 years to bake, and so now in about 2023, I think we can start to say linearsolve.jl, nonlinearsolve.jl, and integrals.jl. These things have all kind of met their maturity level, right? In the 2020 time frame, I think that some people here might have adopted things right out of the gate where they go, oh, this is cool and new, but it really has now taken the time so that way we could say, okay, it has the features that we want. It has native solvers. We have benchmarks on the native solvers. The benchmarks on the native solvers say the things that we've created within linear solve and nonlinear solve, they're faster than the things that we were wrapping in the first place. So you can stick to the whole Julia code and have the functionality, and you are good, right? We are there for nonlinearsolve.jl and linearsolve.jl. And we are there in a sense for integrals.jl because a lot of the native Julia tools for integration do well. And so we've done quite well in those core solver packages. For time reasons, I'll skip over a few things more on the timeline there. I do want to mention, though, that there is one piece in the story of the numerical solvers which is not quite up to speed with some of the others, and that is optimization.jl, right? So optimization.jl, we kind of got late into optimization. You see that this actually started in 2017 or so. And the reason is because Julia has a lot of really good nonlinear optimization tools. So for a long time, we just said, optimization, that's a space of jump, and we don't need to touch it at all, right? And then we started to say, well, okay, there's so many packages for doing global optimization. There's NLOpt, evolutionary.jl, metaheuristics.jl, blackboxoptim.jl. So let's create an optimization package which is over all of the global optimization packages. So we called it galacticoptim.jl. It's like, more than global, it's galactic, right? And so we're just like, yeah, this is just for this one space, right? And then it started to say like, oh, we also need to do local optimization, and sometimes we need to use optim.jl because it's BFGS, and sometimes we have to mix that with neural network methods like Atom and such. So let's start to piece those together. And what we started to realize was that we're just writing a whole, we're also in the game of nonlinear optimization, right? And so that's when it was renamed to optimization.jl. And so this was only done in like 2021, 2022. And we connect it to the JUMP ecosystem so that way we can have all of those available tools. But really then we're going into 2023 and saying, yeah, we need to really take this nonlinear optimization space seriously. And so all the things that we do in the differential equation solver is saying, oh, we have automated, sparsity detection. Well, we should be able to do automated sparse Hessian detection, have our own algorithms, not just algorithms that are wrapping these C codes for, NLOpt, but we should have our own implementations of BFGS so that way they can be natively GPU compatible. All of those same things needs to then come into play for the optimization space. And so that's really ongoing, and we really want to get optimization.jl to be the level of differential equations.jl. And it's definitely not there yet, but it is one of the core pieces that we'll be doing in the near future. And yeah, I'm going to need to give like 8 of these talks. So there's also everything to say about modeling toolkit.jl, right? Which started much later in the system, but we had some very early versions of symbolic interfaces, and then through the time now we've really been spending most of the time trying to get up to, can we make it so that way we can automate the process of solving a DAE effectively and stably? And about 2022 timeframe, we're able to say, yes, solving a DAE, we can transform it into something that is good and stable. And now we need to work on scalability, right? And so the next 2 years were just the scalability problem with JuliaSim compiler. So that way, all the things that we do symbolically, we can generate code that scales to the hundreds of thousands of equations. And Yingbo has been really hard at work on that, and he really has solved that problem. And so the next thing is, how do we make it so that way the entire organization can use symbolic numerics effectively? This is all the work on the symbolic indexing interface, and then also the things about integrating partial differential equations into this world, because right now everyone who's doing partial differential equations does not use the symbolic interface. They go directly to the numerical solvers, and so they lose on all the symbolic optimizations. But that was because we couldn't scale the symbolic interfaces until very recently, but now there's a whole lot of work to make sure that all the PDE things actually can use the symbolic interface. And so that's going to be a lot of this work going on in the near future. I'm not going to be able to talk about, these are some of the slides that I have from Yingbo on, how we can take very large models and then regenerate loops on them and be able to optimize them automatically. Folks that are interested in things like loop vectorization.jl, the guys who work on loop vectorization.jl are the ones who have been building all the symbolic compiler tooling as well. So so there's a lot of nice stuff baked in there. Yeah, and I'm going to be running out of time. So I get to again, there's a SciML talk, but in half an hour we can't even get to anything on machine learning. But I think that one of the things I want to point out is that a lot of the integration with differentiable programming, we've been working on many different methods for how you differentiate solvers over the years. We recently put out this review with some of the folks in the audience here, and it really goes into a review of, here are the 20 different ways that you can differentiate solvers, and here's how they work, here's the different scaling, here's the trade-offs between them and all. And so we've really started to take the effort to be able to write down how all of this works. And yeah, so I'm going to be running out of time. So what was skipped? Well, everything that was in my slides, and then I also didn't even go into anything like SciML PDE solvers, jump processes, uncertain quantification. I think the point to get across with this talk is that the state of SciML is the thing is just huge now, and there's a lot of things going on. So I wrote down these slides, and it was basically like, oh, what are the ongoing projects in the organization? And it was a list of 100 things because we have over 100 contributors, right? And so, yeah, for more, we'll have to have follow-up discussions, and there's a lot going on. I'd love to talk with anyone about what you think is the most important. We'll have a birds of feather tomorrow, which is where you get to brush me about, like, oh, I thought, are we going to work on this? Are we going to work on this? We're working on everything. So thank you very much.
Yes. Yes, so I think it's time that we have our quiz break. with me as an intermediate now, and my name is Sebastian Persson, and I'm a PhD student from Sweden, and I'm going to talk about ptab.jl, which is basically a Julia package for setting up parameter estimation problems, basically defining the cost function. And just to get us all on the same page, I will start a bit with my background and what I mean with parameter estimation. So I am in the research field of systems biology, and in this field we typically build models of our biological systems in order to try to rationalize the data we are getting from experimentalists. And often these models can be translated to systems of ordinary differential equations. And when it comes to ODE modeling in systems biology, there are many challenges associated with them. And one of the main challenges is that typically the model parameters, you can see there on the left side, are unknown. So in order to see if our model can describe the biology at hand, we need to estimate these parameters. And the way we typically do that is that we gather some experimental time-lapse data, as you see here. And then we typically have some start guess parameter value. We run some optimization, that is the parameter estimation, to try to find the parameters that best fits the data. And often the situation looks something like this. We do not really fit the data perfectly. So we need to iterate. We need to build new models to increase our understanding of the system. And often this model building is a very iterative process with many models. So therefore I would argue that one of the open challenges when it comes to parameter estimation is how we can fit the models to data as fast as possible. That is how we can fail as fast as possible, because you should never underestimate the importance of failing fast. Besides faster computations, other important challenges when it comes to parameter estimation is how you integrate different sources of data. Often we use quantitative data, but ideally we should be able to use qualitative data. And another open challenge is how we handle really large models that are realistic. This is currently outside the scope of most simulators, but maybe we can use surrogate modeling here. So what our goal was that we wanted to develop a software where we can kind of support all of these features that are worthwhile research directions. And as a starting point, we wanted to focus on achieving stable, fast, efficient parameter estimation. And a relevant question some of you in the audience might have is, why on earth do we want to have a package for setting up parameter estimation problems in Julia or setting up the cost function? Because the SciML ecosystem is, as Chris just talked about, pretty nice in this regard. You have a lot of flexibility. And the thing is that it's easy to set up your parameter estimation yourself if you have a simple case. So for example, if you have the time-lapse data I showed in the previous slide, you can literally do this in 4 lines of code, and this is probably auto-differentiable, so all your problems are solved. But the thing is that in many real-life applications, things are a bit more complicated. So usually we have multiple observables. We are measuring data for different states of the ODEs at different times. We can code this ourselves, a bit more complicated. Usually we have different experimental conditions, which means that we are measuring data for different control parameters of the ODEs, so you need several forward simulations now. To make things funnier, people like to have the model at a steady state at time 0. Imagine you are giving a drug to a system. This system should probably be stationary at time 0. We can still code this ourselves, but you see, it's getting a bit more complicated. There are also some small dangers coding things yourself. For example, in the literature over the years, we have learned that it's often more efficient to estimate the parameters on the log scale. You can add this, but you need to be aware of this. Also, when you do parameter estimation, you typically want to have gradients. And if your model is small, you can probably use forward diff in Julia, a forward mode, a very nice method. But if your model is large, you probably want to use some reverse approach like Zygote. And people here probably know that getting your code to work with Zygote in a perfect manner out of the box, that can be a quest. So I think the take-home message here is that we can code our objective functions ourselves, but we might miss out on optimizations. And another questionable thing is if your code is reproducible. I would not want to send this to someone unless I dislike that person quite a lot. And it's questionable if it's correct. I mean, this code is not going to work, it has 3 bugs, but there might also be silent bugs that are very hard to notice. And this is why we wanted to develop the package ptab.jl. Which brings me to the package itself. So ptab.jl is a package for creating cost functions or objective functions in the Julia language. And we want to make it accessible to people who are working in Julia, but also those who are working outside. Which means that when it comes to the models, we allow users to support, or rather provide, their dynamic model as a catalyst reaction system, an ODE system, or an SBML file. We also allow users to provide the parameter estimation information in a standard format, table format, or code it directly in Julia. And to make the entire modeling pipeline easier, we provide wrappers to the optimization package for fitting the model to data, but we also provide wrappers to Bayesian inference packages such as advanced HMC, which are the algorithms used in Turing. And as a software package, ptab supports many things, but not everything. So what we have on the pipeline is also adding support for scientific machine learning, but also fitting stochastic models to data, which is a bit harder task. And as a package, ptab has several benefits, and I would argue that one of the bigger ones is that we support different model formats. So everyone here might not be familiar with SBML. This is probably good for you because it's a very tough standard. But it's basically a standard format in systems biology, so it's a machine-readable language for models. The idea here is that you can create a model in SBML, submit it to a journal, and then other people can import this. It's reproducible. And SBML import is handled in ptab via SBML importer, which is a package that was born out of ptab. And how it works is that it basically imports your models into catalyst reaction systems, which allows for many things, such as stochastic simulations or deterministic simulations. It's also a very thoroughly tested software. So it currently passes around 1,270 cases of the around 800 test cases in the SBML test suite. So this basically means it supports most of the SBML features. What we are not supporting, that we are not passing, are like delayed differential equations or events with delay. But if you really want these features, just submit an issue, and I unfortunately have to implement it. And when it comes to the syntax of SBML importer, we try to make it as easy as possible. So the package only exports a single function, load SBML. So you only need to provide your model file. Then it will give you a past reaction network, callback set with model events, which then can easily be simulated, for example, as a stochastic differential equation or as an ordinary differential equation. Besides supporting a standard format in your model, we also support a standard format when it comes to your parameter estimation problem. So the name ptab, which I actually don't remember what it stands for, is a standard format in the systems biology for formulating parameter estimation problems. So basically, what you need to do here is that you need to provide a model, an SBML file, and tables that contain all the information you need to do parameter estimation, such as measurements, observables, the standard information. And once you do it, it's very easy for us to pass the problem. You just need to provide a YAML path, which basically binds the ptab files together into a ptab model, and then the ptab model can become a ptab ODE problem with good default choices. Then you can create an optimization problem, and you can just fit your model to data. And I mean, I strongly encourage people to use standard formats because this makes things more reproducible. But we also recognize that maybe not everybody wants to work with, SBML files. So we also allow people to set up the parameter estimation problems themselves in Julia. And here, we allow the model, your dynamic model, to be provided as a catalyst reaction system or as a modeling toolkit ODE system. And I know this is the old syntax for modeling toolkit. We are in the process of updating to version 9, but we are waiting on Catalyst, which is our core dependency. Besides providing your dynamic model, you also need to provide other minimal information. So you need to provide which your observables are, which you do via ptab observable. And here you can basically provide it as an algebraic formula. So we have that this obsum is basically that you're observing your enzyme E and your substrate enzyme complex. You can make it as nasty as you want here, and then you just provide your measurement formula. You also need to provide which parameters to estimate, because typically you don't want to estimate all the parameters in your dynamic model. This is done via p-tab parameter, where you can also put a prior if you want to do maximum a posteriori estimates. Then you just need to read your measurement data as a data frame, and you can bundle all of this together into a p-tab model. You can create a p-tab ODE problem, and you're done. So overall, we try to make it packaged as accessible as possible when it comes to setting up the problem. Another benefit I actually consider to be quite a good benefit with the package is that it works with likelihoods, so you're working within a good statistical foundation. So this means that when you are fitting your model to data, the cost function that is generated by p-tab is a likelihood function, so you're going to do a maximum likelihood estimation. Besides actually being statistically robust in this sense, you're also going to have other benefits, like you can do identifiability analysis to assess uncertainty in your parameters, model selection using likelihood-based tools like AIC or BIC, and sensitivity analysis. But also, if you're doing Bayesian inference, and if you provide priors, we can do Bayesian inference with algorithms such as those in adaptive MCMC, advanced HMC used by Turing, and also pigeons, which are all something we provide wrappers for. So besides setting up the problem and doing the modeling pipeline, we also have some fun things on the inside of the p-tab package. And one is that we probably spend too much time thinking about gradients. So if your model is small, we support gradient computations via the forward diff package. And this is often the most efficient approach for models with less than 75 parameters. And we also done some internal hacks that makes it possible for the package to be faster than naively taking forward diff from your objective function. We also recognize that sometimes model can be large, then we need to use adjoint approaches. So we also wrap the adjoint sensitivity functionality in the SciML sensitivity package. If you don't care about these things, we have gradient methods for small and big models. Also, we integrate with the rest of the SciML ecosystem, so we have access to ODE solvers for both small and big problems. And to see why this is a benefit, we can take a look at this plot here. So what you're seeing here is the runtime for 29 benchmark models sorted based on size. And this is the CVOD BDF solver. It's quite famous for being the workhorse in a lot of established software like Amici, LeBroner, D2D, industry standard. Here you're seeing the runtime for the Rodas 5P solver. It's a Rosenbach solver specialized for smaller models. And you can see that at least for the smaller models, it has quite a good advantage. And if we look at the accuracy here, we can also see it's actually more accurate if you use the same tolerances. So I think this kind of nicely highlights why we want to have these kind of toolboxes in Julia, because then we can also choose an ODE solver that is specialized to a problem we are actually working with. Lastly, as a benefit with the package, is that I also would like to argue that it's a fast package in the spirit of Julia. And I always think that, standing in front of an audience, presenting, saying that you have a fast software without any additional evidence is a bit too bold of a statement. And something fun we could actually do in this project is that we could do quite a thorough benchmark. Because the thing is that p-tab, it basically imports a standard format. So this means that we can also compare against other tools, non-Julia tools, that also import standards formats. In particular, we could do a very thorough benchmark against PyPesto, which uses Amici as a simulation engine. And here I want to highlight that Amici is a very efficient C++ wrapper to the Sundial CVOD library. It does a lot of fun things like model pre-processing via SymPy. So in short, it's fast, it's been thoroughly tested. I think it's a worthwhile thing to compare against it. Also, we can make sure that our benchmark is relevant. So in this study, we only decided to benchmark against real models with real data from the p-tab benchmark collection. So we're going to have all the fun things with, for example, model misspecification. And the first thing we wanted to benchmark using this approach was the gradient computation runtimes. Because the thing is that when you do parameter estimation, just as in machine learning, you want to have the gradients. And computing the gradient is substantially more expensive than computing your objective function. So this is actually your computational bottleneck. So what you're seeing in this plot is the runtime for the BERM benchmark model with 2 different Julia ODE solvers against Amici, 2 different colors. And hopefully you can see, if the screen is big enough, that for the BERM model, PTAB is approximately twice as fast when computing the gradient via the forward diff package. Naturally, we looked at more than one model, and in general, we saw for 14 out of 90 models that we benchmarked, the PTAB was often between 2 to 3 times as fast when it came to computing the gradient. So basically, this highlights that using forward diff compared to the traditional forward sensitivity approach seems to be more computationally scalable. Another benefit with using automatic differentiation is that we can also compute the second order derivative, the Hessian. And here we can look at the scaling behavior by looking at the runtime ratio between the objective function and the Hessian. And we typically saw in our benchmarks that this ratio is smaller than the number of parameters squared. This is quite good scaling behavior because this algorithm is quadratic in its complexity. And having access to the Hessian when fitting models to the data can also be very beneficial. And to see why, we can take a look at this plot. And here you are seeing what we like to call a waterfall plot. So when we are fitting models to data in systems biology, we use a pretty naive approach. We have 1,000 start guesses, and then for each one of those, we run parameter estimation. Then we record the final objective value. And you want as many runs as possible to reach, that valley in the end, because that often indicates that we found the global optima. The results you're seeing here are from using PyPesto with FIDES, which is a Newton trust region method that would be awesome to have in Julia, but it's from Python, with a Gauss-Newton Hessian approximation. Here you see the same results when we use FIDES with the full Hessian. You see that more runs converge to the global optima. And we can also see that we get even better results if we use the interior point Newton method from the opt-in package. Some people might argue in this case that maybe we don't need a full Hessian because we still have sufficiently good performance. However, for some models, this can actually make quite considerable difference, as we can see here for the Fujita benchmark model. So what I primed you on here is basically parameter estimation results for 2 models. But naturally, in our benchmark study, we wanted to evaluate more than 2 models. And when it comes to evaluating parameter estimation performance between 2 softwares, this is a bit of a tricky task. But the way we decided to do this is that we used PTAB and we used Amici with the same optimizer, the FIDES trust region method. So we're using the same optimizer, but different simulation engines. And again, we can see for the BERM benchmark model that we were approximately twice as fast. And this is something that held in general, that for 15, or rather 16 actually, better than I expected, 16 out of 19 models, we were often between 2 to 4 times as fast when doing the parameter estimation. And I would argue that there's actually only 2 models where we are really outperformed. But runtime is not everything when you are fitting models to data. It's also important that you have good convergence properties. And one way you can measure this is by looking at the runtime per converged run, and then you can normalize this score across models. And if you do that, you achieve something that looks like this. So the way you read this plot is that you look per column, and here the brightest yellow dot corresponds to the setting that performed the best. And then you look, or per row probably, row column, yes. And then when you look across the columns, you see across models. The short story here is that for 15 out of 19 models, PTAB.jl achieved the best score. For 2 models, it's very hard to draw any general conclusion because very few runs actually converged at all. For 2 models, we are totally outperformed, which is also, area for improvement. But in general, I think this quite nicely highlights that as a Julia package, even compared to other state-of-the-art packages in systems biology, PTAB.jl achieves good performance when it comes to fitting models to data. And naturally, I would always be more happy to talk more about this package, but in the interest of time, I think it's time that we move on to the conclusions. So basically, in this talk, I presented 2 Julia packages, PTAB.jl and SPML importer. They both work within an ecosystem that is based on setting up cost functions for fitting models that are driven by differential equations to data. And my research field is systems biology, but I mean, this is a general thing. As long as you have a model that is driven by a differential equation and you want to fit it, this is where it works. And typically, when we decided to do a realistic benchmark against other state-of-the-art tools, we saw that PTAB as a package achieved state-of-the-art performance, at least for models with less than 100 parameters, which are the ones we thoroughly benchmarked. However, when it comes to developing software, you're never really done, so I think there are some relevant improvement areas going forward. And what we want to add is that we want to add more utility functions to make it more user-friendly. Probably after the workshop yesterday, I also need to update the documentation. We also want to add a Bayesian inference benchmark. So we are currently benchmarking different Bayesian inference ways to doing inference of the posterior. And if anyone works here with, for example, Turing or something, I would be happy to discuss different algorithms in the context of ODEs. What I would like to have in the package, however, which is also a bit outside of my scope at the moment, but would be very nice to have, is more efficient ways of computing the Hessian. Because currently in PTAB, we are computing the Hessian with a forward over forward approach. This is quadratic complexity. We did some benchmarks recently where we were horribly outperformed by Diffrax, which is a YAX-based differential equation solver, because they can do a reverse over forward, or forward over reverse approach. Moreover, where I think it's, at least for us, a large area of improvement is doing a Jones sensitivity analysis. Because here we are also outperformed by Diffrax, so I think this is also an area where we could improve even further. Both packages are also available on GitHub. You can download them as normal Julia packages. If they are useful in your research, please give them a star. It would help me, especially when writing postdoc grants. The benchmarks I presented today are hopefully soon published in a paper. Last year on JuliaCon, this paper went under review. Next year on JuliaCon, I hope I can say that the paper is no longer under review. But we shall see. Review number 3 is a bit slow. And naturally, the work I've done here could not have been possible to do alone. So I just want to acknowledge Fabian, Stefan, and Jan for helping setting up the benchmark that we did. For the package development, I want to highlight Rafael, but also especially Torkel Luhmann, who helped a lot with the Catalyst integration with the package. Also Swedish Lab, which is kind of the research group I am part of, and SFF, which are kind of the funding agency that gives me money to do this. So with this, I think we are on time, which means that we can move on to any questions. I choose.
Yeah, thanks. I was wondering if this always works, or if there are certain characteristics of or your solver or your equations that that the optimization becomes difficult.
I mean, if your optimization problem is very, very hard, like you have an oscillatory model, it's questionable if we are going to be able to fit the model to data in a satisfactory way. But as long as your model is a differential equation and you put up into the PTAB framework, at least we should be able to compute the objective function and your gradient. So you can always set up the problem, but then depending on how easy it is to fit the model to the data, we can't guarantee that you're going to be able to fit it without maybe using specialized methods. But for setting up the problem, we have wide support.
Okay, but no guidelines or already first.
We have guidelines in the documentation for which settings we recommend for certain problem characteristics, which optimizer we recommend. And once this paper finally gets published, we will have even more guidelines.
Okay, thank you.
Yes.
Yeah, 2 main questions. So first question is, what's the reason why you're not using the forward over reverse Hessian? Because that's existed in SciML sensitivity since like 2019.
I didn't get it to work, and I spent too much time on trying to get it to work.
Okay, we should talk about that in soon then. The other thing is, what's the reason for not using similar least squares optimization methods, right? Because you're comparing a BFGS method, which is a general nonlinear optimization method, to a nonlinear least squares method, right? The Gauss-Newton approach. The Gauss-Newton approach can actually make a few optimizations. So the fact that you're faster means that you're still doing more work and you're still being faster than them is actually that's quite nice. But I mean, what's the reason for not using, say, truss region Gauss-Newton from nonlinearsolve.jl rather than using the BFGS approach?
Actually, I think you got that bit a bit slightly incorrect. So we are actually using just the Gauss-Newton as an Hessian approximation, so we're not working within a least square framework within any software, either PyPesto or PTAB. But the reason why we didn't use the truss region method from nonlinear solve is because we are working with bounded constraint box constraints. And at least when we started to do these benchmarks, Optim was the relevant package, and the truss region method in Optim doesn't work with box constraints. And I don't know if the truss region method in nonlinear solve at the moment works with box constraints. If it does that, we would be very happy because we are looking for that kind of algorithm. Because what we have seen generally is that we need to have the constraints, bounds, because otherwise integration failures.
Yeah. So that works through a transformation approach. Well, we could talk more on that one as well.
Yes. Yes.
Okay, I think I might have missed this part, but when you were showing the models, you were when you were defining the models earlier, you used catalyst and a symbolic model with a differential equation.jl. Does this also work for the old notation for differential equation for differential equations that were in symbolic models?
No. So we want to have the model in a symbolic representation, either catalyst or as an ODE system, because that makes it much easier for us to bookkeep all the model parameters. Because if you code it like input vector p, then you know which p is which.
All right.
Maybe you then.
Very short. Do you support constraints between the parameters?
Aha, you mean one parameter is less than a...
Yes, or one parameter is 2 times another, or equal, or similar.
No, but we should, and it shouldn't be that hard to do it, so I would always be happy to discuss that, because we also have the optimizers that should be able to handle that. Yeah. So I think we're done.
Hello. All right. Welcome, everyone. So this talk is now going to be on docs, CI tests, error messages, and interfaces in JuliaSciML, right? So what do I mean by this? So what I really mean by this is that the TLDR of this talk is that SciML has formalized many processes, right? We had an inflection point in 2022, and in the State of SciML talk, I kind of described a little bit about that inflection point where, we changed from being Julia DiffyQ to SciML, but then a lot of other things had happened at that point too, right? We had a lot of companies that grew up. Pumas AI was, founded in 2019, and then by 2020 it was being used for the Moderna vaccine, and beyond that, it just it started growing fast. With Julia Hub, we started growing, and we started using things in a lot of safety critical applications. And we had the whole MIT Julia Lab grow up, and the number of contributors grew for other reasons. And so it couldn't just be a small organization anymore where it's like, oh, we run a few tests, and then then after you run your test, you let the package go and see if it works out, right? It's like no. So it had to become a whole enterprise of just how do you make sure the entire thing stays maintained, right? And so because of this, we needed all benchmarking. We couldn't just say, hey, let's benchmark it and then post your benchmark results. We need to start to be able to say the benchmarks need to be fully reproducible, so that way we can all update the same benchmarks and we can keep a timeline of all how performance changes. So that way, if someone makes a commit that makes something code go slower, we know exactly what code did that, and that was either a choice we made because it's like a correctness improvement, or it's something that we need to revert, right? And so we need to make it so that way, did you break anything is not just a small unit test. It's did you break anything here? Did you break anything downstream? Did you make anything go slower? Did you make it so that way putting code onto robots, embedded code onto FPGAs, did you make that harder, right? Every single detail like that, we need to be able to understand from every single change that any contributor says, oh, hey, here's a PR that fixes a typo, right? We need to know all that information, because it's not, because Julian and SciML is being used in so many places that we have to consider all of this now. And we need to make it so that way a contributor who knows nothing about most of those applications, their code is being worked and tested like that, right? But not only that, but we need to make sure that the documentation then works as a system that is not just on a website, the standard documenter, but how do we make it so that way the documentations all talk to each other, so that way if you work with the differential equation solvers and then we say, hey, we're referencing something over in the symbolic library, how do you make it so that way you have these cross references between a few hundred libraries? You have to be able to build them all together, right? And you need to have error messages that target non-experts, and you need to have your interfaces be strictly defined. And I think that last piece is a huge piece that a lot of people might not have even known that we've done, right? So in 2016 or so, we wrote some blog posts about how, hey, look, in the OD solvers, you can put anything in there, and any number tends to work, and whoa, you could just find out whether code works just by letting generic interfaces work, right? And there's still a lot of generic duck typing that we do. But now all of our interfaces are strictly defined and tested, and there's certain guarantees that we are able to put on code if it satisfies the interfaces, right? So we've really built up our own interface system throughout SciML, and I'll be talking a lot about the formalization of the interfaces. And so there's a lot of stuff that we used to say back in 2016 or 2018 or even 2020, which is just, no longer true about the organization. Now the organization, it's run as a machine with, literally machines checking if you don't break any interface assumptions and all that, right? So I want to talk about how we've done all this, because a lot of other organizations can adopt our approaches, and so we want to share what are the things that we're doing and what are things that every other Julia code should be doing, right? And we kind of want to scold you for not doing some of these. There's a complimentary talk. There's a talk that I gave back in about 7 months ago in Erlangen on maintaining large-scale Julia ecosystems. It is not the same talk as this at all. It instead talks about 7 axioms for maintaining an extremely large-scale organization, and the high-level points to think about. I'll call that a complimentary talk that you should go check out if you're interested in this kind of content. So again, I just gave the State of SciML Organization talk, which explained what is a SciML organization. But the key thing here that I want to highlight is that the organization is huge. There's hundreds of unique contributors every single month. And so what do we do in order to make sure that the code that comes out of here is reliable and it works everywhere? And, and again, since we're talking about hundreds of contributors, we literally do, the people who do the package management statistics, right? They told me that before they got up to that State of Julia talk that they're like, yeah, we calculated out, how many releases are being done, but we realized that the SciML organization is making 3 package releases a day on average. Right, so there's so much code going out that there's releases going every single day. So how do you make sure that when that's happening, that every single new patch, everything's working, right? So what are the rules, right? So how do we even make this work, right? So one of the key things that's really happened is that we've had this SciML style guide, right? And so we say the SciML style, it's a stylish guide for stylish Julia programmers, right? What it's all about is this is exactly how you should program. And there is a section that is about like, oh, here's how you format code. Like when you do a doc string, your doc string should start with, if it's a type, then this is what a canonical doc string looks like. And so that way when people give a pull request, we don't tell them like, oh, I don't have to go in there and say, oh, here's how I would do this. It's like, read the SciML style guide and come back when it's matching the style guide, right? So while there is a section on syntactic formatting, I think the thing that's more important about the SciML style guide, which if you haven't seen it before, would be very useful, is that the majority of it is dedicated to higher level style choices about how to code effectively for performance and maintainability. And so it's all about having these axioms. And I just want to, what do I mean by that? Here's one of these axioms that we put there, right? Always default to constructs with initialized data, which means, there are constructs that you can do where you say, I create a vector of undef, or I use similar. But if you use those operations and you have undefined memory, and there are certain bugs that could happen down the stream that are hard to find. So therefore, always default to using things that are writing actually zeroing the memory, except if you can prove that you have a performance benefit for that. And if you have a proof that you have a performance benefit from that, you better also give me a CI test that says that it's still faster. So that way, if it's not faster in a Julia version, we can also make sure that we initialize the data at that point. Right? So this is one of these axioms where you just say, if anyone ends up using similar in the code, we say, no, it shouldn't be similar, it should be zero. You should zero that memory, unless you can prove to me that you actually are faster with the uninitialized memory, right? So this is one of these high-level points, but actually the SciML style guide has a whole lot of these points, right? Things like avoid any operation that is called unsafe, avoid eval, closures should be avoided. Why should closures be avoided? Well, because there's a boxing rule with that can happen within, So some of these are related to the way that Julia optimizes code and the way that the garbage collector works, and we say, these are certain styles that we use, or these are certain styles that we avoid, because we know that this gives you code that is better for static compilation, code that is better for compiling to WASM, code that is better for compiling to GPUs. All of these things need to be true about our code, so we need to make sure you have a style guide on the code that makes it so that way it's not just, oh, hey, it works for my computer. It's like, no, it's got to work on Windows, it's got to work on Windows 32-bit, even if you don't use it. It's got to work on ARM, it's got to work on GPUs. And so this is a style guide where if you follow the SciML style, then things will work pretty well universally. But we then have to make sure we write it down so that we share this with everyone. And so these are the rules. And if you want to know each of these rules in detail, I'd be happy to chat about any of them. They all have an explanation as to why it's there. Sometimes it's limitations of LLVM, sometimes it's limitations of Julia's optimization, optimizing passes, and sometimes they're fundamental limitations in computation. So we established a whole bunch of rules that we throw onto everybody. Then we also have callprac, right? So we have this library called the Contributor's Guide on Collaborative Practices for Community Packages, which basically says all the things that you should do when you're contributing to a SciML organization package. Now, there's one thing I wanted to highlight in this list, which is the continuous release process, right? So callprac, as what we do as an organization, and the way that we found to be able to make the scalability work, is that we establish a continuous release workflow for the organization, which means after a pull request, your code should be good enough that we should be able to release with it. And this is one of the reasons why we have so many releases, right? Because if we take in a new feature, well, we should be able to release it and give you that new feature. Nobody should be checking out the master version of our package for a month, because then we actually have to do something with you, right? So I remember like early in 2018, we'd say, oh, hey, check out master, and if you want to use this new feature. And then what I actually would find is that user was still on the master branch 2 years later, and they're like, oh, I found a bug, I found a bug, and it's like, how'd you find that bug? It's not even released code yet. Well, you told me to go on master 2 years ago. We're like, no. Only use released versions of packages. We will release features immediately when they are ready. Which means, but we always release from main, which means that things can only merge if they are release ready. And so this is the continuous release process. When we merge PRs, we do a release. Merge a PR, do a release. And it has many advantages because you basically know that everything on main is fresh. If you merge a PR, what are all the new features in that new release? It's only the things in the PR you just merged. Like everything is much more local, and then users are never told to go off main. And we also have all these checkpoints as to every single version. So then everyone, if there is something that is a regression that shows up, we can know exactly what version is involved there. And the thing is then that the only way to get things done then is to be able to take really big idea PRs and break them into small little chunks. So that way you're chunking out one little feature at a time, which makes it a lot easier to be able to get, a lot easier to be able to get things maintained, because you're no longer saying like, oh, we're going to completely change this entire package in one pull request. No, we're going to do small changes one at a time. And if you can't do small changes, most likely the reason why you can't do small changes is because you are completely breaking interfaces, and we need to talk about this. Right? So it really discourages people from doing things that just completely break anything. And that's really what we're looking for when we're going for maintainability. So those are the rules that we've established, and it's really helped us a lot. And the next thing is all about documentation. So so what do we do about the docs? So the real question is, how do we make a few hundred packages look like they're actually one unified set, right? The way that we've done this is that in 2023, we released this global documentation where the documentation of all the packages are put together into a single form, so that way they have cross references within the search bars. So if you're using, you say, you're using differentialequations.jl and you see a part of the tutorial that is telling you, hey, use symbolics for sparsity detection, you will then get a reference over to symbolics where it will tell you this is where this function is defined, right? Because again, there's a whole ecosystem, right? You almost can't even think about a package on its own, because when you use the differential equation solver, you're also using linear solvers, you're using automatic differentiation tools, and so we had to really bring all the documentation together into one system in order to make that make sense. And then we had to establish a lot of core documentation principles. Since I'll be running low on time, I won't go into all of them. But the key thing, though, is that we always are putting a getting started tutorial on the top. And every single Julia package should do that. The first thing that you click on should be a getting started tutorial. And why is that? Well, what we found through the package analytics is that 90% of people will only look at your first tutorial. They will skip all of your, it doesn't even matter where in the manual things are, you can put all your manual pages on top. They will go to your first tutorial. 90% of people will read that first tutorial, and that will be what they think of as your entire package. I now have, I have the Google Analytics for over 100 Julia packages here, and I can tell you that literally every single package, doesn't matter what order we had the documentation in, everyone already did that. So we moved that to be the first link on every single documentation, and we made sure that every single core functionality that we want people to use and everything that we want people to know about this package better be in that first tutorial. Everything else is useful other pages, right? But 90% of people will only ever click on that first tutorial. And I know I'm looking at people in the audience who are laughing. You're saying, oh, I do that. Yeah, you all do that. So the analytics don't lie, right? So there's other things to do about, I guess one other point to make in the documentation is that we've really separated out the idea of tutorials versus examples, right? So tutorials are about showing a functionality of the package. And the point is that you want to make the example as small as possible. So, every tutorial has the smallest differential equation definition possible. It tries to be like 5 lines of code. And then you say, oh, you want to use ensemble threads. We show you how features work, right? But then the other thing that happens is someone just goes, well, in all of your tutorials, you use ensemble threads, but then the threading's not actually faster. And we're like, yeah, because it's only like one ODE, and like you need a big enough model. So this is where you have examples, right? So tutorials show you how to use features, so that way, it's a very nice, succinct code that shows you how to do something. And then your examples show you like, oh, here's a gigantic model, and we do multi-threading on it, and so therefore it's faster, right? And so if you separate those two ideas, then it becomes much easier to be able to say, hey, yes, we have the gigantic examples, but the gigantic example is not infiltrating, I don't have to have, all this MPI code around just to be able to show you, yes, here's how distributed coding works, right? So separating those two has really helped out a lot of our documentation. And here's just a few examples. So like, so the difference between a tutorial and an example is like, we have a tutorial on the left where you say, hey, we use the Lorentz equation. Like we use the Lock-Voltaire equation, the Lorentz equation almost every single time. Why? Because there are 3 ODEs and everyone already knows them. That makes it easy to be able to talk about things like, okay, how do you set tolerances? I don't need to have a 500-page ODE definition to be able to tell you how to set tolerances, right? But you want to go see some other examples. You want to start talking about deeper features and sparsity detection. Yeah. Okay, we have another page that goes into those and shows you how to make use of those deeper features, and we separate those two to make it so that way it's much more legible, right? And so you can see that and then some of the examples go into things like oh, how to use the symplectic integrators. Yeah, there's also a tutorial page that covers the same topic, but the examples show you how to do this in physics. It shows how to do this in biology. It shows how, and so like you can really hit all those terms that people are looking for in terms of specific parts. And some plan changes that we want to do is that there are some nicer ways we could show these examples. Instead of having them all in the sidebar, we could have nice pictures for these. And it turns out that there is this demo cars.jl, which Morten had been building within Documenter, so that way you can list out all your examples where you say, here's a picture representative of it, like Kepler problem. You show a picture of orbits, and you have a nice description under it, and you can have all these cards for it. We don't have this integrated into our documentations yet, but this is what we plan to be doing with our examples, because right now there's just a sidebar that says like examples, and just has them all listed out, but we plan to be reformatting that in the very near future. So I do want to say that, writing a documentation is basically the same as writing a murder mystery TV show, right? You think about like a CSI TV show, you want to start with a cold open that sets the stage, and it's like, oh, here's everything that's cool. This is the getting started page, right? You just say, here's everything that's cool in the package. Put the sunglasses on. Yeah, the opening to CSI. But after you do that cold open, you play the theme song, right? Which is just showing a bunch of examples really quickly. Like you could do this, you could do this, you could do this, you could do this, you can do this. If you think about like the theme song of a show, it just shows you very small clips of all the things you can do. When you finally get into the meat of the show, you write these big tutorials that is like, okay, here's one story, here's one story, here's one story. And then you have the manual after all of that, right? Like, the page of just all the doc strings, that goes after all of that, because most people don't want to read that. It's like most people just don't want to read doc string after doc string after doc string. You should have it, but most of the things should be contextualized as a story that is then walking people through why these features are there, right? So keep up with time. I'm going to get to the testing part. So here's the thing, right? So we have hundreds of repos, and one of the things that happened in the last year was, for example, the CodeCov organization changed their policies. So that way, if you had 20 pull requests or 20 jobs that happened within an hour, they would throttle you. And since we have a pull request open probably about every 5 minutes, we got and that opens up 10 or 20 jobs itself. We were basically throttled into the point where CodeCov is no longer usable when they made that change. And so we had to go to every single library and update the CI process. That meant that it took about a few hundred PRs just to be able to update our CI because one system changed. So what we've done instead is we said, okay, let's centralize our controls. So what we can do instead is you can have a repo that is called the .github repo within your organization, and you can put your standard CI scripts there. And what it ends up looking like, I guess we don't have a picture of that, but what it ends up looking like is you just say, my test.yaml file for my CI, its definition is go look at the .github repo. And so we basically have now most of the organization's CI scripts just say go look up at this one other repo. And so we can, in one space, we can change the way the CI works for all of the different packages in the organization at once. And the thing that is nice about that is it means that every single package is being tested and being, having the same test setup and everything in the same way. And so, for example, when the new LTS changes to Julia version 1.10, we can in one part of the organization make a change, and now all of our packages update the LTS. The latest or the last release that we test on will be 1.10, right? And so if you are having issues trying to maintain large numbers of packages, I check out how this .github was set up by Anant, and this is something that a lot of other organizations should use as well, because if you start to be able to say, oh, every single package has its own CI scripts, then you also have the problem of some of them will test on Linux, some of them will test 32-bit, but they won't all be testing the same thing, right? And you really want to make sure that gets unified. Another big thing that we've done is a lot of environment-based test parallelism, right? So within the CI test, we specified that we're going to run the test over a bunch of what's known as groups, right? That sets an environment variable that we then read within the CI script. And so then within the CI script, it just checks, is the environment variable group equal to interface 1, equal to interface 2? And what this means is that we then just spawn the test strip with these different environment variables, and then it'll run then on that subset of tests. So for ordinary diffie-q, I think it has like 20 different test sets. And so when someone creates a pull request, it will automatically spawn 20 different CI jobs, each of them with a different environment variable, and thus each of them only running a subset of the tests, which means that each of these jobs that are created are all in parallel running one small set of the test suite. So the ordinary diffie-q tests take about 6 to 7 hours to run in total, but you don't actually see that because each subset of it's like 15, 20 minutes. It's just running on a whole bunch of different machines at the same time, and it's very easy to set up with just using environment variables. And we also have the special build kite, which is what we use for any large-scale GPU jobs or for any gigantic tutorials like diffie-q flux. Takes about 3 hours because it wants to show you how to train neural networks and neural ODEs. And so therefore, we have a special CI machine that's set up that just is continually using its GPU to be able to retrain the same neural networks over and over and over, because it's also a good test for did anything change or fail in the training. Well, we can check whether the documentation build failed. We also do downstream tests for everything. So I would encourage that everyone steals our downstream.yaml. It's a really nice file. If this file exists within your repo, then what will happen is that anytime anyone opens up a pull request, it will also do testing of your downstream users. So why is that the case? Well, because for example, in SciML base, that defines how ODE problem is defined, which then every solver from ordinary diffie-q to stundials, all these solvers use that same type definition, right? So if we change that type definition, we don't want to just do my test pass, but did I break anything in any solver, right? You use this, you use this, you use this, you use this. And what the downstream.yaml lets you do is it lets you be able to say, these are all the packages that I know are closely related to this one. Let's make sure that none of them break from your PR. And that gives us a stronger definition of breakage, right? It's not just, did my test break? But it's also, did anyone who uses my package, did their test break as well? And if you start to put those tests on, people are much more reluctant to make a breaking change, which is a good thing. Because then you say, okay, if you do want to do breakage, then we will do the proper response of we will have to bump the major version. But if you bump the major version, well, it is now for you, the person who made this PR, who broke the thing downstream, you have to go make a PR to the downstream package saying, I'm sorry I broke something. Here's the fix for the change that I just made as well. This is one of the policies that we've implemented, and that makes it so that way, if breakages actually happen, the packages that are relying on that piece of code, they should get a pull request from us. They shouldn't find out 1 month from now that, hey, something broke. I need to go find out what these SciML guys did. Like, you should actually get a pull request from us that says, we changed this interface. We bumped the version. You got a compat thing that you have to change. Here's the fix for you, right? And we can find out when we have to do that using the downstream testing. So every Julia repo should have the downstream testing put on it. I will die on that hill. We also have automatic formatter suggestions in the in CI. So I mentioned that with the SciML style, we tell you how your code should look. Well, also GitHub will then show you that, hey, your code doesn't actually match the style. Like here's the line length limit. So here's a suggestion how you should fix your code. And so you've been rolling out this automatic formatter. Again, you can steal any of these scripts from us, and that you want. There's also compat helper and tagbot, and what these do is if we do make a change that is breaking, we will bump the major version. And then anytime that a major version is bumped, it will open up a pull request on every single repo that is one of these that is depending on it. And then we'll have a pull request that says, hey, you need to be able to test and make sure that you're allowed to use this new version, right? And so all of this is done fully automatically. So error messages. So in 2022, our error messages were downright awful. We basically just relied on whatever error message was thrown within the code, and that did not necessarily get you great error messages. What we've done now is we've moved all the error messages up to the SIML base layer, so that way very high in the interface, it then is checking if these properties that we know have to be true are true, and then we throw a contextualized error message in order to be able to do that. Some of them go pretty deep. So here, for example, it's checking whether the number of arguments in your function are matching the requirements for the ODE solver, and so we'll check, is there any dispatch that does not match this argument, and we then throw a very contextualized error message that says, we know that a lot of people in MATLAB and SciPy do this thing where they just write out all of their parameters, but our syntax is not like that. Look at this thing, go look at our documentation on that, right? So because we're able to know from years and years of answering people's questions that, you don't just have an error that's just like, oh, hey, I used too many arguments. Almost every single person that was putting too many arguments in the ODE solver is because that's how you actually do things in SciPy. So we should tell them, like, I understand you come from SciPy. I understand you write code like this. But here's, this style in SciPy is equal to this thing in Julia, right? Because most of the time, these are the issues that people have. It's not just like a type, okay, there's a lot of typo things as well. But a lot of times it's this translational thing. And that's something that standard error messages will not get for you. How does the thing that I was doing before, how do I translate it in my mind? But also we have a lot of interface tests in here. So, for example, we say, technically the ODE solver actually works. If you start with float 32 numbers and you change your output to float 64 accidentally, the ODE solver actually works. But in 2023, we put an error message on that to be able to say, you now have a type mismatch because almost certainly you did not do this on purpose, right? And you can see this is an example where you're multiplying a value by 1.3. 1.3 is a double float 64, whereas your values before were float 32. And we say, after the first step of our ODE, your type has changed. You can actually disable this error message, but you probably don't want to be doing that, right? And so by doing all these high-level interface pieces, we can really make sure that people write code that is correct. And then the next thing is interfaces, right? So we have, I'm going to be running out of time, but we've basically taken the time to be able to define every single interface that we have. So, we basically be able to say, if you want your number type to work with SciML, your number type has to satisfy that 1 unit of t times, 1 of t equals da. Like we've gone and written down all of these things need to be true, and we're adding tests to make sure that, your properties of your types actually work out before we even try to hit the solver. And if it doesn't, then we tell you that you're not matching the interface. And so we have all sorts of interfaces: common solve, SciML base, SciML structures, which is an interface on how parameter types should work, array interface, which tells you how arrays should be working, and there's just interface after interface after interface after interface. I will not have enough time for that. But we no longer are in this world of just saying, just throw something into the package and see if it works. No. We have all these interfaces that tell you exactly when things are true and false, and we have functions to be able to check all of that. And you should be defining your functions to that, otherwise we are throwing errors. Lastly, we have continuous benchmarking with SciML benchmarks, which is a fully reproducible benchmark system. If you put a script onto the system, it will automatically run on a computer that we have at MIT, and it will generate all the plots. And we use that then to be able to say nobody runs a benchmark on their own machines. And contrary to popular belief, we do lose some benchmarks, but the reason why we don't lose them is very often is because with a moment we see that we're not at the fastest at something, we tend to get all of our work on to make sure that we're going to be fastest there. Which means give us more benchmarks where we're not the fastest, because that's where we find all of our good work. And over time, we plan to be rolling out per repo performance regression benchmarks. This is already on lux.jl. We plan to be doing that in the near future everywhere. So thank you, everyone. I'm way out of time, but these are all processes which I believe every Julie package and organization should adopt. Thank you.
think, do you think there's any possibility that GitHub changes its policy pricing-wise that would basically ruin everything that you have set up?
It'd be very hard for so because we have our own machines for a lot of our CI processes at this point, because I mean we run concurrently about like 60 to 70 jobs at most time, right? So we do through MIT we do have some this kind of organizational agreement which gives us 60 seats in a larger CI, but even then we way overdo that, so we have to have our own machines. So if GitHub was to decrease the amount of free machines we got, we would just roll out more machines with self-hosted. So I think we're pretty safe, but I mean. But that means, yeah, we've already had to develop a whole self-hosted system, and we can share that with more organizations as well. One of the things that's nice about self-hosted too is that means that we can test on weird hardware like AMD GPUs and Metal and all these other things as well that GitHub doesn't provide. Yeah.
What is your buzz factor?
What is our bus factor? I mean, that's extremely hard to measure because it's different per repository, right? So like the ordinary differential equation solver, there's like, I think like 5 to 6 people who maintain a lot of that. Nonlinearsolve.jl I think has a bus factor of like 3. Quasi Monte Carlo probably has like 2. And then there's some things like SciML sensitivity, I'd say like 1.5. Like, so each repo has a different number. I would say that most repos probably have a bus factor around 3. But there are some repos that we need to work on. But the thing about bus factor here, though, is that I'm VP of one company, I'm director at another company, also at the MIT Research Lab. So anytime we have a problem, it's just like I need more people to work on SciML sensitivity becomes a problem of I'm going to get someone at JuliaHub that is now forced to do this. So Daria, you're now working on SciML sensitivity, right? Like so like it's open source, but at the same time, by having all these different organizations involved, there is an element of we can hire someone for that, which is very helpful that we weren't able to do when it was just a smaller open source organization. Yeah, thank you.
to pick? Does it work? All right, cool. All right. Good afternoon, everyone. Yeah, thanks for coming to this talk. I am Alexander Demin. I am currently an undergraduate student in Moscow at HEC University. So I will talk to you about the new functionality in our package, structural identifiability.gl. The rough plan is that I will describe you what is the problem of structural identifiability, then we'll show you how you can analyze it using our package, and then we'll show you this cool new feature that you can now use. Right, so let's get started. So, roughly speaking, structural identifiability is a property of a dynamical model that determines if a parameter in the model can be recovered uniquely from the measured data. So let's say I'm a practitioner, I want to model some phenomenon in nature. I cook up some exponential growth model, right? So I write x of t, which is some process in time, and I write a, which is some time-independent unknown parameter. I conduct an experiment, I measure x of t. Now the structural identifiability answers the question, if a, this unknown parameter, can be recovered uniquely from the measured data x of t. So in this particular case, you can see that, well, the parameter, there is just a direct formula. If we can measure the data ideally, and the derivative of the data can be computed without any errors, we can recover the value of a uniquely. So in this case, we say that the parameter is structurally identifiable. Okay, but let's now look at the opposite, at the interesting situation. So this example was probably quite unnatural. Right, so let's talk briefly about non-identifiability. The setting is absolutely the same. We still have some ODE, we have some process x of t, and time-independent parameters. Now there are two of them, right, a and b. So the question is the same as well, right? So can we recover the values of a and b from the data that we measure? So let's say we have some real world data, we conduct an experiment, we have a time series from 0 to 1 over t, and we measure some values x of t. Right, so the question what do you think, like, if values of a and b can be recovered uniquely from such data? So, well, just by looking at the equations, you can get a rough idea that if we swap the values of a and b around, the measured output actually doesn't change at all. So we can, in no way, from the point of view of the person who measures, we can distinguish different values of a and b from each other. So, and we can kind of, we can see this if we construct the graph in the following way. Right, so let's just take values of parameters a and b in some grid. So we take a and b in some square grid, and we plug them into ODE, we solve the ODE, and we can plot the error between the real data and the data that we have just estimated. Right, so on the graph on the slide, you can see basically on x-axis is the value of parameter a, on y-axis is the value of parameter b, and the color is the magnitude of errors that we get between the real data and the estimated data. So, and you can see on the graph that there are basically two symmetrical points, right? So two symmetrical sets of parameter values that give us the fit of roughly 10 to minus 25 error, which is almost 0. So one of these points is the point that I used to generate the data itself, this data in the time series. The other one is a spurious optimum that could hinder our practical identifiability analysis if we decided to use some optimization method with such a loss function landscape. So in this case, we would say that parameters a and b are structurally non-identifiable. Okay, so now to the package structural identifiability itself. The package was developed by Gleb Pogudin and Ruven Don several years ago. So later it was enhanced multiple times by Ilya Ilmer and other contributors. So the package supports modeling toolkit, supports formulations of problems with Catalyst, thanks to Torkel. And so the usage is fairly simple, right? You just import the package, describe the model in some simple domain-specific language, and you put, well, basically you put all your outputs that you observe in this y equals the output that you see. Now you can just pass the model to the assess unidentifiability function and get some nice output, some nice result. So let me just decipher the output on the screen a bit. So for each quantity in the model, we get some verdict. For x, in this case, we get globally, which means that the quantity is globally identifiable, everything is nice, we can uniquely recover the value of x of t for all possible t. But that is quite obvious because we measure it. So for A and B, situation is a bit worse. We only have local identifiability, which means that we can have up to finitely many different possible values for A and B, which is exactly what we have seen on the previous slide, right? Where we had at least 2 different points which give identically good fit. So one crucial thing that you can note from this slide is that you do not actually need any data to perform structural ineffability analysis, but it still can give you some useful information. So structural ineffability is a property of the model itself, in a sense. So in the light of the previous talks about practical parameter estimation, where it was mentioned how important it is to quickly iterate over building models, it can be quite useful to quickly reject some badly formulated models this way without conducting any experiments. But this is ancient history, so it is the classical ineffability analysis. So now let me show what was developed recently in structural ineffability, and so what can be used now. So structural ineffability now provides a new function, a reparameterized global. This function accepts an ODE and outputs an ODE. This function tries to eliminate all non-identifiability of quantities that it can discover in the model. As a side bonus, this function can reduce the dimension of the model. So let's look at some example to see this more precisely. So here I have a standard SIR model studied a couple of years ago in the paper. So we have several states, several parameters, as the number of susceptible people, and so on. So we can call this classical identifiability analysis under 1 second on my laptop, get that, well, basically all of quantities, most of quantities are non-identifiable here. Okay, so the question is then, well, what we can do about this, right? So it's a fairly simple model, but still there is a lot of non-identifiability here. So this function reparameterized global basically accepts an ODE and spits out 2 useful pieces of information. Right? So you give it an ODE and it gives you back a transformation of your variables that you need to apply to the ODE to get some new ODE. Like on this example, you can see that well, for example, B divided by n times A was mapped to A3 and so on. Right, so the function basically tells you a transformation of variables that you need to apply. And then it also calculates the new ODE for you. Well, the variable names are a bit convoluted, but they can be recovered, of course, because they are in direct relation to the original ones. So you can notice right away that the new model has fewer parameters, right? 2 fewer parameters in this case. And, well, the additional nice thing is that all quantities in the new ODE are globally identifiable. So which was the goal from the very beginning. All right, so to conclude, non-identifiability, so the unappreciation of non-identifiability can impact negatively the practical parameter estimation. Structural ineffability provides a way to assess identifiability, and also provides these cool new features you can try out to reparameterize your model to kind of assist the practitioner to deal with this non-identifiability. Okay, I thank you for your attention. I'm done.
did you say it now supports full modeling toolkit models as well?
Right. Right, so it supports ODEs and discrete equations, so it doesn't support anything more complicated than that.
Like a-causal systems. So if you create a model through an a-causal, could you still perform the structural identifiability on it?
Well,
Yeah, I mean that was the structural identifiability.jl because you just end up with a differential algebraic equation system.
Yeah.
And then you can apply it to the flattened system. Yes.
Yeah.
Yeah, so a-causal models right after structural simplification give you a flattened differential algebraic equation, and the structural identifiability tools do work with the DAs, right? They kind of write them in a slightly different form, but there's a translation process that is within the package that does that. Yeah.
Thank you, Chris. Yeah.
All right. Yeah, everyone. Okay. Yeah. Good afternoon, everyone. I'm Max de Rooij. I'm a PhD student in the Department of Biomedical Engineering in Eindhoven University of Technology and Eindhoven Artificial Intelligence Systems Institute. And I will tell you about my recent work with SciML about personalizing models of human blood sugar using SciML. All right, so first we'll start with some relevance of the project. So the Netherlands, you might know it from cheese and tulips. The Netherlands also has a lot of pre-diabetes. So it's about 1.4 million people, which is 7% of the Dutch population, is estimated have pre-diabetes, which is a stadium that precedes type 2 diabetes and is characterized by elevated blood sugar, and also is correlated with a lot of health problems that occur and have a significant burden to the healthcare system. And one of these things is they have a 9 times higher risk of developing type 2 diabetes. So what we want to do about this is, we want to enable the personalized treatment of prediabetes, but for that we need to measure how healthy someone is. And one of these things, measuring health, is difficult. So it's very difficult to quantify how healthy someone is, directly. Another thing is that the development of prediabetes and type 2 diabetes is very slow and is also very heterogeneous. So every person can have a different trajectory in how they develop bad control over their blood sugar. Also, the effectivity of the interventions is really determined by how fast it's detected and how fast the intervention is applied, really. So one of these things that we want to try and do is to measure this health by measuring the state of the glycemic control, so the control of your blood sugar in the human. And we want to do this using a model. And the idea of the data that we use to quantify this is that someone consumes a liquid test meal. In this case, it's what we call an oral glucose tolerance test, which is just water with a lot of sugar. And we measure the blood sugar profile over time after someone has consumed this meal. And using a model, we can then quantify the status of someone's glycemic control system. And I said model, so what kind of model do I mean? So one of these models is developed here about 8 years ago, which is the Eindhoven Diabetes Simulator, or Eindhoven Diabetes Education Simulator, it's also called, but here we're not using it in education context. So That's why I left it out. And this model is a differential equation model that describes the uptake and and actual release of glucose and insulin in the human body, and after one of these test meals. And using this model and the data, we can perform parameter estimation, and these parameters are then able to quantify someone's health in a personalized health space. All right, so this is very nice, but these models also have some trouble with some people, especially like in this case where we try to estimate the parameters. If the model shows this type of curve for someone, then we're not sure whether these parameters can actually quantify someone's health very well. So, and one of the reasons that this happens is because the model currently uses a PD-controlled insulin production term. So this is a term from more control engineering that also works in a thermostat, for example, to control the temperature in your house. And while it works very well on some people, it also gives results in these types of behaviors. And to mitigate this, my research was about how can we improve this personalizability. And one of the things that I tried was to include a neural network as this production term. So we model insulin production using a neural network, and to improve the personalizability of these of this model. So, all right, this is a nice goal, but we first also want to know whether these neural networks can describe a biological system properly with quite a low amount of data, because usually these measurements have like 4 time points. So it's quite difficult also to make sure to see if they work. So first, what we did is we did some tests. So we made a universal differential equation of a different system. This system is basically a substrate S and a product P that's converted. So the substrate is converted into the product using a specific type of kinetics, which we call Michaelis-Menten kinetics, which is also the term that is replaced by this N in the model equations below. And then using quite sparse data, we try to fit this neural network model to this data. And then as a result, you can see on your left, or on your right here, that it kind of works while we have data. So the gray area represents the area where we actually have data for this system. But afterwards, these models go crazy. So what you can see that while the blue one goes down and the red one goes up, you can see that somehow it is encoded in the system that there's a conversion between the two, but it's not captured very well to this system. So we also wanted to solve this, and by that we added an extra term to our loss function. So we regularized this system by kind of preventing the system from going below 0. And you can see that only adding this loss function actually quite improves the model fit also beyond the data. So this is one of the results. And then, all right, so as I promised you, we also tried to do this on our insulin production. And we actually see that within this model, while we have some neural networks that learn a kind of a biased term there, which is indicated by this gray constant line, we also have quite some neural networks that describe the insulin data very well, and the glucose data is also described very well on average. However, I was talking about personalized models, and this is actually on an average data of a population. It's also quite a lot of data here. So, well, for that, I'm going to leave you in the dark because I have not a lot to show on that part. So it's still ongoing work there. So we show that it works. We can actually fit these models quite well on sparse data. And this regularization can improve the reliability of these neural network representations. And in population data, these neural networks can estimate the insulin production term. However, for future work, we want to add multiple populations, see if we can estimate this in different populations, and we can personalize these models. Another area of research that we are looking at is to reparameterize these neural networks and use symbolic regression to actually get interpretable equations. This has become quite a challenge there as well. And the last part is to validate also these model predictions in multiple data sets. With that, I want to thank my supervisors, Natal van Riel and Shauna O'Donovan. And if you have any questions, I'd be happy to answer them.
Hello. With regards to type 1 diabetes, do you see any application in terms of predicting blood glucose levels to then apply insulin?
Yeah, good question. Yeah, so type 1 diabetes is a bit of a more difficult case for these models, because on one hand, it's very difficult to predict how someone responds to insulin directly, because the insulin sensitivity can still vary between people, but because there's no insulin production or limited insulin production, it's also very difficult to quantify how much glucose is taken up in response to insulin, because you cannot. If someone is living with type 1 diabetes, you typically don't want to give them a test meal with 75 grams of sugar. So it's also kind of difficult to get these measurements, and also because there are a lot of different types of exogenous insulin that also kind of work in different ways. There is quite a lot to be done in that area to actually be able to quantify that. So I'm not actually actively working on that. We do have colleagues that work on type 1 diabetes specifically. So yeah, I can refer to them if you are very interested.
Thank you.
Well, thanks for your talk. It was really interesting. I saw you had very few data points. So I guess that you weren't measuring with the patches. There are some patches, I think, that measure also the glucose level, but a bit more in an imprecise way, I think. Are the results different if you measure it like this with more data points, or like you're doing now?
Yeah, so on one hand, for these models, we also need data on insulin, and unfortunately, we don't have these patches that can measure insulin yet. Nevertheless, if we would have them, that would be really nice. But also, we note we have done some research on these patches, basically on these flash glucose monitoring or continuous glucose monitoring sensors. Because they are also measuring glucose in a different part of the body, we also see that the response to a meal is different from when we measure it in the blood directly. So we'll need some conversion there as well.
Okay, thanks.
I'm Avinash Subramanian. I work at Julia Hub, and I would like to talk about JuliaSim HVAC. So HVAC standing for heating, ventilation, air conditioning, refrigeration. So JuliaSim HVAC is a platform for performing thermal fluid modeling and composing that with the SciML ecosystem. So first of all, just HVAC systems compose sort of three different fields. So there is the fluid mechanics, there is thermodynamics, and then dynamical systems. So kind of like presenting an overview of an HVAC system. So in a room, what a user would see would be the evaporator. So the box somewhere in the corner is just one of these pieces. So that's the piece called an evaporator. And then behind the scenes, there is a refrigeration loop. So the main goal of an air conditioning system is to remove heat from like inside a room and in some way move that heat against nature, so against the temperature gradient, to the outside of the room. So by making use of work in the form of compressor inputs. So the main pieces of an HVAC system are the evaporator, the compressor, so the refrigerant gains is pressurized and gains some temperature, and then it is able to lose heat in the condenser. So this is the part that is usually the part of the air conditioner that is put outside the apartment with a fan usually, and that releases that heat into the atmosphere. And then there's a valve to close the system. And one like graphical way of understanding this is through this pressure enthalpy diagram or energy diagram. So like down here at the bottom, there is a gain of removal of heat from the room, and then at the top here is discharge of that heat to the environment. So it's a very quick overview of the fluid mechanics, and just to show how this generalizes to other similar systems. So behind the scenes, we implement a 1D Navier-Stokes equation and have like a finite volume discretization. So this is like mass, energy, and momentum balances. And we have the capability for two-phase flow because like evaporation is from liquid to gas. We also need to account for a bunch of other fluid mechanics phenomena such as compressible flow, turbulent flow, viscous dynamics. So all of these are present in the HVAC system, and obviously heat transfer. So the next thing I'd like to show is that all these, like the modeling of all these fluid mechanics phenomena tend to create a bunch of numerical challenges. In particular, they yield stiff and discontinuous dynamics, and also so this requires special like adaptive step size solvers, and we also need robust DA initialization procedures. So the goal of the JuliaSim HVAC platform is to abstract away all of these complications from the industrial user. So the goal is to just present the industrial user with what they need. So we present like three main features at the moment, which is pre-built components. So we have pre-built heat exchanger, valve, compressor, and so on components that a user can drag and drop and just present what they need to present. Configure just what they need to configure, and then all the mathematics and differential equation solving goes on behind the hood. We also provide fast and accurate spline-based thermodynamic property models, and these tend to be like 3 to 4 orders of magnitude faster than querying calls on equation of state-based, like a full equation of state-based system. And we have a robust ecosystem, which I'll present. So next, just presenting a quick demo of this, which I hope is clear. So the first thing is one would import the HVAC package, which is available from Julia Hub, together with a bunch of other open source packages, modeling toolkit, SAML base, and so on, data interpolations, and so on. Next, one would load the refrigerant medium. In this case, they usually have these names with R32 as an example here. So this loads the splines. This is also provided directly from by HVAC. Then one can set initial conditions. So here's an example using Pluto sliders. There's obviously a code-based version as well. And in this case, I would like to also set control inputs. So as an example, let's say you are turning on the air conditioner. So that's like a really quick ramp up from zero, from cold start. And then maybe it's not cold enough, and then you turn it on even more, and then because you want to take out more heat from the room. So this is just one synthesized control trajectory that that can be used. So HVAC provides a bunch of the API has a bunch of for instance, for the compressor, one would have like a typical compressor, and one would like declaratively put in the initial conditions that are relevant, the configuration that is relevant. And similarly, there is a typical LEV for the valve, condenser, and evaporator geometries can also be geometries, and all those parameters can be inserted as I show here. Next, as is typical with modeling toolkit, one performs structural simplify, and we see in this case. So this is a relatively simple, like stylized case, and the full system has about 1,200 states in the DAE, and after structural simplification, it hits 70 states. So then one formulates the ODE problem and initializes and solves. And typically, we are able to solve in less than a second, primarily leveraging these fast spline interpolations and adaptive solvers from a SIML ecosystem. So to debug, we also provide a bunch of canned plots. So for instance, this is a pressure and pressure enthalpy plot. So when we turn on, so these dynamics are what go on behind the scenes when we turn on the air conditioner unit. So the compressor creates this pressure lift that allows for temperature flow. So I would like to say a lot more on calibration, but there's a talk, a 30-minute talk on Friday, entirely talking about how to connect an HVAC model with a model optimizer for calibration, both static and in 5 lines of code. So the roadmap is to compose this with multi-domain systems, so particularly batteries, HVACs, drivetrains, buildings and HVACs, acceleration using surrogates and controls, and so on. So that's what's going on. Thank you. Sure.
Thank you for the presentation. I was wondering how you make sure that you don't connect elements which have, for example, different refrigerant, which have different like inherent properties. For example, two different refrigerants, it cannot exist.
At the moment, we only have one like global refrigerant that can be loaded in HVAC. There is the modeling toolkit also supports this idea of domain connectors, which is meant to be the way of making this more extensible. And sometimes you might want to have like 2 separate refrigerant loops with 2 systems. So the idea is to extend to use those semantics.
So, good afternoon, everyone. My name is Vinicius Santana. I'm a postdoc at the Norwegian University of Science and Technology. And today I'll be talking about process simulator.jl, a differentiable chemical process simulator. So, as a chemical engineer, I'll be talking about chemical process engineering, of course. So yes, my name is just like the Real Madrid player, Vinicius, Vini Jr. So a lot of people ask this question. So since we are in the Philips Stadium, I thought it to be relevant to say this. So, so before starting actually about what we are proposing, it's always a good idea to say a few words about the past, because every time we have an idea, we think that we are the only one having this idea. This is definitely not true most of the time. So people in the past, in the 50s, they started doing process simulation. So of course, they were most cared about steady state simulation because, you know, they only cared about dynamic systems in the case they had to shut down or start up the plant. And then in the 70s, the ASPEN project at MIT marked an important part of chemical process engineering and simulation, actually, that led to the very popular ASPEN company and their products. And then in the 90s, people started to begin, you know, they started caring about dynamic simulation. First, because they went out of large-scale production of commodities to more specialty products, which require semi-continuous operation. And then, of course, a lot of some companies appeared to cover this need of the chemical industry. So, for instance, the Speed Up project, which then evolved to GPROMS in Imperial College, is very good at doing dynamic simulation for chemical processes. And also in the 90s, there was this DIVA that you know, rised in University of Stuttgart. And then EMSO, which is also a dynamic simulator that appeared in Brazil. So, while some of these software became commercial products, when you go to the open source software side of chemical process simulation, the story is not that, you know, happy. So in 2008, we have the WSIN. We're very focused on steady state simulation. So the developer is Daniel Wagner, and he named the simulator with his initial, which is amazing. And then in 2016, we have also the IDAS project, which is very nice, supporting also steady-state flow sheet simulation. So they say they can do dynamics, but yeah, there's no single example in the documentation about dynamics. And then in 2019, there was an effort in OpenModelica, so named OMChemSim to do also chemical process simulation in OpenModelica. So they have a very nice support for dynamic systems, as the whole Modelica ecosystem has. But there was very minimal support for thermodynamic calculations. So that leaves the question, what's coming next in terms of open source, if anything is coming. But then the goal of this talk is to show that, okay, we can do something with what we have in Julia right now. Well, why would you choose SciML to build the open source chemical process simulator? So we have this nice declarative symbolic modeling language, mtk.jl, that makes easy going from math to symbolic representation and later to a numeric implementation of chemical engineering models. So we have these nice causal component-based modeling where we can just compose our process unit operations into a flow sheet. And also one of the most important parts of chemical engineering simulation is the physical-chemical property prediction, which Claypron.jl has been doing a great job in implementing state-of-the-art equation of states for chemical engineering. Of course, as I'm mentioning, one need of the current chemical engineering industry is the need of dynamic simulation. So in this sense, we can count on differential equations.jl, which has a lot of very high-performance implementations of ODE and DAE solvers. So now I'm going to jump to show some things. Well, so I made a critic about dynamic simulation in the past that they only use to start up simulation, and I'll be showing a demo about the startup of a reactor. So I'm assuming no isothermal reaction with a cooling jacket. And also, we are assuming also flow-driven simulation. We assume that we can perfectly control the inlet and outlet flows in the simulation. Well, the synthesis is water, propylene oxide leading to propylene glycol, which is a very important chemical product. Well, this is typically what how we represent a CSTR, continuous starter tank reactor. So we have water and two reactants, water and propylene oxide. We have some solvent leading to our product and some remaining reactants in the reactive mixture. Well, the dynamics of this system is quite simple: mass balance and energy balance. A lot of time in the effort in chemical engineering is spent actually in this piece here, which is equation of state. But people, when they're doing dynamic simulations of the system, they say, hey, let's ignore this and simplify the properties, and then we can only focus on the dynamic part. It turns out that a lot of science goes into this, but when people gonna do dynamic simulation, they just say, hey, you know what, I'm not gonna care about this. So, to simulate this, we're gonna need a material source object, with properties calculated with Claypron, and also a CSTR object, and also with inside of it, we have a kinetic reaction object. So, the material source object, if any of you had the opportunity to use Aspen or any flow sheet simulation, is basically you define a stream, you specify what substance you're using, pressure, temperature, composition, and flow rate, and then you get a lot of calculations to specify enthalpy, entropy, a lot of free energy, Gibbs free energy, Helmholtz free energy, gas phase fraction, a lot of properties. So we are also doing the same here, using Claypron implementations of equation of state. Well, so we have a system with a lot of polar substances, so we have to use an equation of state that support polar substances. So polar PC-SAFT is one of those. Well, here I'm just instantiating a Claypron model. I'm specifying the substances, I'm loading some properties, and then I can instantiate my PC-SAFT model with water, methanol, propylene glycol, which is the product, and this is propylene oxide, another name for it. So the material source goes as, so I can specify the substances, I specify the thermodynamic model, the pressure, the temperature, the molar flow rate, and also the composition, and then modeling toolkit generates a bunch of equations calculating any other property derived from these pressure, temperature, and composition. Then we can go to the CSTR object. So we can build a kinetic reaction. So we have a simple first order reaction. We assume that the kinetics is controlled by the concentration of propylene oxide. I can specify a bunch of properties. So there's the pre-exponential factor. This is the activation energy. This is the stoichiometric coefficients. There's the exponent that goes in the parallel of kinetic reaction. So then we can build the CSTR object. We specify the substances, the phase at which the reaction happens. That's important. So we only have one inlet stream, so that's why we're specifying just one inlet port. And we're giving some gases the concentration at T equals 0. That's important as well. So then I'm connecting the source object with the reactor object using the connect command from modeling toolkit. And then I can build the system and then name it my connector. And then you can see that we have a well-posed problem with the same number of equations as unknowns, which is important. And then we can simplify the system by calling structural simplify. That goes from 194 equations to, I don't know, 12. So 5 differential and 6 algebraic. And then we can do some analysis. Oh, sorry. Okay, we have to specify initial condition. So basically assume that the tank is full of water and we have some propylene oxide, which is one of the reactants. And then we can solve the differential algebraic system of equations using one of the solvers that differential equations.jl have. And then we can do some analysis. Well, in the startup, the temperature reaches about 360 Kelvin, which is something that someone carrying out the startup policy for the reactor should be concerned about. Otherwise, you can end up in a very dangerous situation if you don't know what happens when you start up the simulation. And then we can also plot the concentration of our substances over time. So we have the limiting reactant that goes up and then drop about to 0. It's being consumed, which is nice. And we have our product being produced and then reaching a plateau of about 2.5 kilomoles per cubic meter. Yeah, that's the phase plane. Another analysis we can do. I mean, we can go all over the day plotting the properties we calculated with it. So with this, I end up my talking. I have no more time. So thank you for your attention. Anyone has questions? I think chemical engineering is not interesting.
Thank you for your talk. I saw a lot of numbers in the presentation, but they didn't have units from Unitful or one of the other packages. Is it possible to combine, to use those units from Julia?
Yeah, I think that's one of the things we want to do as well, because in engineering, it's very easy to make mistakes in the units. So having this way of checking those, it's something we want to include it. Yeah. Thank you.
So, oh, now you can hear me. So I'm Marcus. I've made a package with two of my colleagues from university. We're from the Technical University of Denmark. They were not here to help me present, and I don't think we have time to be more presenters anyway, so probably really good. It's called Physics-Informed Regression, and essentially it's a fast way to compute parameters from modeling when modeling with differential equations. So first of all, like most of you will know what the inverse problem is. We've also gone through it already with with you, so I won't go too much into it. Essentially, if you have data of what's it called that is described by some dynamical system, we should be able to estimate the parameters that were used to that best describe the behavior of the data, we have already a ton of ways to do this in the SciML what's it called ecosystem, but I'm proposing a method that that rather than using nonlinear regression, just uses a least square an ordinary least square estimate to get quick results. So first of all, I'm not going to go too much into math. We don't have time for that, and no one wants to hear it anyways. So I'm just going to explain what are the assumptions of the framework. Well, first of all, the system can be nonlinear, but it should be linear in terms of the parameters. Because essentially what happens is the symbolic system will be rewritten into a matrix vector equation, evaluated for each observation, and then there exists a global minimizer or a global optimum for the parameters, which can just be computed with one iteration of linear solve. So I assume most know how to set up dynamic models with differential equations, so I won't go too much into that. But that's with this new symbolic framework. It's super clean, and for these examples, these are very ideal examples that I'm working with. So I'll just be working with simulated data and trying to recreate the parameters that were used during the simulation of the data set, and see if I can find those. My package is essentially just these two lines of code. One, to approximate the derivative from the data, and another one is essentially just the regression framework, or the regression algorithm, that takes as input the symbolic model as defined on the previous slide, the vector of states for each time step, and the corresponding derivatives. The algorithm takes about 30 milliseconds, 40 milliseconds, so super fast. And it should be mentioned before I try to make it seem better than it actually is. This is ideal conditions. So This only works because you can create a pretty good approximation of the state derivatives. In practice, if you have noisy data, you will need some other kind of strategy to approximate derivatives for the state, some smoothing strategy or something like that. In here, I'm just doing spline interpolation on the data and then getting the analytical solution from the spline derivatives. Yes. What else? I also have, Chris, you mentioned that there are also always 3x. You always go with lot capital theta as a prime example, and also, of course, the Lorentz attractor as one of the other examples. So I thought I would have that as well on the slides. It's of course it's a way more sensitive system. So even with relatively accurate estimates of the parameters, you will the trajectory will still diverge over time from the if there's just a small difference in estimates. Originally, we found this method by when working with COVID-19 in back in 2021. So I also included the SIR model, which was is essentially the original, what's it called, project we worked with, as mentioned. Yes. What else? Well, the neat thing, something that is also super neat, but that is just in general with the SciML framework, is that with Catalyst, it's super easy to also what's it called, convert systems to convert reaction models into these symbolic models. That all just can be passed as input to the physics informed regression algorithm. So if you're not a big fan of ODE models, you can just do a reaction network and still fit the data onto the model pretty neatly. This is just a simulated example. That's why there's someone. But it's the two last lines of code that are the same two lines of code as actually always will be. Well, just to quickly compare with. Oh, I have plenty of time. I thought I was. Oh, nice. Oh, I've been rushing through this. I guess there will be more time for questions, and that's nice. Well, the packages that already exist for doing this. There are of course many, but I'm just going to mention some of them here. Of the diffect parameter, which is essentially just a simplified what's it called, framework for you solving this exact problem. And that it does in fact use nonlinear regression, which is more where you have to supply an objective function, and it's in generally way more robust. But of course, it requires a nonlinear optimization algorithm, which takes longer time to run. The alternative strategy is to use something like Cindy, which is also not only parameter model regression, but also model discovery. And the idea that we had for this algorithm is essentially just another way to interpret Cindy, which is to do the exact same algorithm but constrain it onto the the known model. So it's Cindy without model discovery, but essentially just including the model fitting onto the data. Yes, that was it. Any questions?
Yeah, thank you. If I remember correctly, Cindy used some variational regularization for calculating the derivatives, especially for noisy data.
Yeah.
Could you comment on how your implementation works on this?
Well, mine is definitely way worse. I have looked at the Cindy implementation, and I was just wondering if I should just import that into my model to use that for more accurate derivative approximations. But I haven't done that. So this is just my own kind of worse version of a derivative approximation. But of course, that would improve the performance, because right now it seems like it's good, but as soon as you have like less frequently sampled data with high noise, then calculating derivatives like this will not work, or will give really bad results.
Thank you.
Anyone else? Yeah.
Yeah, thank you for your presentation. So one of the issues with I typically see with these type of regression methods is, what do you do when you don't have data for all your state variables? Have you thought about looking into something like that?
Yeah, I was actually thinking about that. Well, you should be able, in that case, then I was thinking if I had more time, I would do it so you can supply some, you choose which state variables you want to supply, and then it'll only, what's it called, use the part of the matrix, the original matrix rewriting, that include those state variables. And you can still do the fitting, but of course there will be some parameters, of course the parameters that depend on those equations will not be estimated correctly. If that makes sense.
Yep.
Yes. Yes.
Thank you for the presentation. I'm sorry you probably said it, but can you use irregularly spaced data as an input to your algorithm, or?
Yeah.
Great.
As long as you have derivatives as well, approximations for those, what's it called, those values. Anyone else? No? It's good. That went super fast. Okay.
Okay, yep, sounds great. All right, so I offer to try to make up some time, if we can. We'll see if this works. I give these presentations in a lot of different versions, so I might be able to get us back a little closer to track. So I'm Erin Aquesta. I'm a mathematician at Sandia National Labs. I'm a part of a large U.S. Department of Energy consortium focused on the next generation of infectious disease modeling. For that reason, we're doing a lot of work. And I'm just waiting right here at the title slide to emphasize that I shifted my title a little bit to say this is towards the development of hierarchical calibration. And what I'm going to offer you is a design of how we're using Julia SciML ecosystem to represent these high-fidelity agent-based models in a way that allows us to decompose global and local parameters. So let me motivate where we're coming from. As a community here, I don't think I have to overly emphasize that the COVID-19 pandemic really highlighted a lot of challenges that we had for computational modeling. One of the things that we noticed is that we have an opportunity in the 30 years of history at Sandia in particular, obviously I'm biased, but the whole Department of Energy complex, where we have extensive background in developing these large-scale, multi-scale, highly verified, accurate and rigorously calibrated complex systems. So we wanted to bring that to bear in partnership with the advancements in scientific machine learning to allow us to be able to provide novel solutions in the age of exascale computing, where we're able to add more and more functionality. How do we also support rapid calibration in a situation in which we know what's going on, but we don't quite know what's unfolding in front of us, like we were in 2020. So another aspect where I like to motivate the conversation today is the US Government Accountability Office came out with a report shortly after the onset of the pandemic to emphasize the fact that early in the response, this is when we need the best models to help inform our policymakers. The models are not actually accurate or well calibrated until, and I'm moving around like everybody can see me, but I forgot that there's folks online, right? So my apologies. Nope, that's not gonna work either. But early in the response, the information of the models could be most useful, right? But it's not until afterwards that we can have the best calibrated models. So we're working to figure out how to preserve the information we have about dynamical systems for how infectious diseases spread across a host population while being rapidly adaptive to a novel situation. So there's many different ways, many different models that are useful at different phases of an outbreak. This just highlights a couple of them. It's not to imply that you can only use these models at those different stages, but these are, we go from the highest level of assumptions all the way to the left, to the highest fidelity models up there with our agent-based models that capture a lot of the nuances and the localized behaviors and effects of what's happening. And we want to be able to bridge that in such a way that we can work from those population scale homogeneous dynamics of our Bayesian inference and compartmental models. Compartmental models are your system of ordinary differential equations that give us that quick development and rapid predictive forecasting frameworks, and be able to use the information we learn at that phase and integrate it into the next phases, where we're getting into the network graph-based models and those higher fidelity agent-based models that are capturing these specific details of the entire population that's unfolding for a policymaker. Because truly, at the end of the day, you walk into somebody's got to decide whether or not they're going to put their city, their town, their state into lockdown. You give them an ODE model and they're like, wait, what is this? It's so abstract, they have a hard time understanding what's going on. You walk in with an agent-based model and you show them how their city's unfolding, and you say, hey, that's your local grocery store, and that's your school, and this is what happens when you lock them down, right? It's a lot easier for them to use, but we have to be able to make a better approach to rapidly developing and calibrating those models so that they're useful to the local decision makers. All right, cool. So we talked about just now why it's important to be able to have those higher fidelity models with all the specificity that a decision maker may want to understand when they're making a decision what the impacts are going to be. But what is it about the other models that are so useful? Well, there's so much. There's about 100 years of knowledge that go into our compartmental models that help us preserve the principles of epidemiology. That once we go to the higher fidelity models, we want to make sure is consistent across the modeling paradigms. So I think at this point, a lot of people have seen the SIR models. These are the system. This gives all the different representations. As we move forward, I keep doing this towards the presentation. As we move forward, I'm going to stick to the flow diagrams that we have there, the simple compartments and how they transition through them. I will not show the full system of differential equations, but there's one example to start. The properties of these models, though, is that we have down below, I'm putting with the associated biological descriptions. So lambda is our force of infection function. Beta is going to be the infection rate, and that's always going to be spreading to the susceptible population with respect to the proportion that is infectious at time t. We also have that 1 over gamma, that rate in which we transition our infectious population into the recovery population. The inverse of that is the mean duration of infectiousness, right? These are biologically consistent parameters that we'd like to preserve. The beauty of this, though, is that implicitly defined inside of that differential equation is that I can find that secondary infection rate. So we hear everybody talk about what is R naught. During the COVID-19 pandemic, we heard it was anywhere between 2 and 4, and that depended on the data for different regions, right? Well, in the model, it has its own R naught. That is the bifurcation of the system. We can mathematically find it, derive it. We would like to make sure that that stays consistent with whatever modeling paradigm I utilize to support decision makers as well. And it's through that understanding of R naught that we get to a sense of what true herd immunity would be. Because R effective is going to be that time varying parameter that takes R naught times the proportion of the population that's still sick. And then through that, I can get to an understanding of what that peak would have to be, where the disease would start to die out on its own because there's nobody really to infect anymore, right? But again, let's go back to these are nice abstract, overly simplifying assumptions that are in those models, the homogeneous mixing, the fact that homogeneous behavior and uniform mixing, I mix those. We know these are underrepresented of the real world, right? So here's an example of COVID-19 for the US from 2020 to 2022, a couple of years. There's a lot of peaks in there. And unless I add a lot more compartments, I'm not going to be able to capture all those peaks, right? So instead, we can jump all the way to the other extreme. and that is our agent-based models. And so I'm going to jump us all the way there first because I want to talk about what we are doing. And so this is a number of the Department of Energy lab collaborators that are working on extending the next generation of infectious disease modeling, taking us to exascale. So Lawrence Berkeley, Argonne National Labs have some of the fastest supercomputers that are at our disposal. And we're able to run these agent-based models at 10 to the 18th flops, which is amazing, right? But with that comes more functionality. We're adding more layers to the multi-scale dynamics. We're getting higher fidelity of host behaviors in there, the multi-scale interactions within the host pathogen dynamics as well, eventually. We can even layer climate on top of that, right? We know the system is far more complicated than that compartmental model can capture. So we're moving in that direction. As we do that, we add more and more parameters. We make this inverse problem a much more challenging calibration problem for us. But I don't want to move away from what I biologically understand about that system. Oh, I forgot I had one more, really describing the complexities here, sorry. So this exascale-ready agent-based model is actually an exascale acceleration from what's called EpiCast that was developed by Los Alamos National Labs, another one of our collaborators. This is a particle physics-based agent-based model that captures individual-based single communities. So I'm capturing every individual of every community based on demographic data and information. We get into single communities so we can understand how people mix within their communities and across the communities. There's commuter flow within there, and then the time steps are only taken twice a day. So there's a daytime and an evening time. And everything else can be intelligently approximated by the sophisticated software developers that I work with, right? We get different types of stratification. We have age stratification, households, neighborhood clusterings I just mentioned. There are 4 types of model parameters in here, the person-to-person transmissions. We have the disease natural history. I'm getting back to there's biological consistencies I do not want to lose just because different regional complexities manifest my parameterization differently. I'm going to anchor us on that type of conversation there. And then there's a lot of variety of different mitigation options. These types of models are great, like I said, to do the scenario analysis. They're projection models. It's going to say if you shut down schools, if you close the access or restricted access to local supermarkets, this is the impact to your community. But I'm going to highlight and focus on the first 2 there. That's the person-to-person transmissions. We can't get out of that. That's what we're modeling. And that's the highest priority parameters that I want to first look at. And then we have the disease natural history. So the latent period is the time after infection before you're infectious. You have the incubation period. That's the time after infection before you become symptomatic. Those are 2 different things. For something like COVID, as an example, you were infectious 2 days. If you were sick with COVID-19, you were in fact believed to be infectious 2 days before you were symptomatic. And that's why if you had a contact tracer call you and say, okay, well, when did symptoms start and what did you do 2 days before that? They were tracking everybody that may have been potentially exposed and were considered your presumptive positive cases. That makes it hard to control a disease like that because self-isolation is not going to work on its own anymore. And then there's the infectious period. And we can capture the percent that we believe to be asymptomatic. I want to emphasize here that when I say asymptomatic, I do not mean the biological definition. When I'm modeling social dynamics, I mean that portion of the population that is infectious or maybe not such a severe case that you didn't think it was just allergies, right? Very often people would think it was just allergies and it's still spreading. Essentially what we're capturing are the people we don't know are spreading the disease. Because they're not a part of my case counts in the data I have available. And then there's a scaling factor assumed with the asymptomatic population, because if you are not symptomatic, then maybe you're not spreading it so readily. Okay, so if I look at those disease dynamics, or if I think about those disease-specific parameters, I can actually start to build a compartmental model that is semantically related. I'm going to say semantically related, not mathematically related, because it's really hard to make that comparison between an agent-based model and a compartmental model on its own. But semantically related, I can start getting at that latent period, incubation period, and infectious period. I'm going to have some dependent parameters there, because when I start to decompose my pre-infectious before symptomatic population, that's that I tilde S compartment in there, then I have to start getting at other different windows of time that I'm trying to capture that aren't specific, but it can be inferred from those 3 specific disease parameters. And so I can start building this up, and what's great about this is I can actually go to the force of infection function and get a quick estimation of what the model R0 is. So I actually know what R0 is going to be and manifest in this model. I didn't know what it was going to be in the agent-based model. So these are some of the characteristics we want to preserve when we start to relate it back to the agent-based model. Okay, so we're going to talk about what that looks like in a second, but I want to get some preliminary details out of the way here. All right, so, sorry, I'm going to go back here for 1 second because I did forget the big orange box in the middle. So this compartmental model that we have, it does not yet capture the heterogeneous complexity of the contact matrix. It's not going to capture the impact on disease spread due to the lockdown. And it's not capturing quarantine and isolation is still missing, right? So there's still a huge model-to-model form error that exists. I'm emphasizing this because I want to make sure we're on the same page about what we mean when we say model form error. So quickly here, let's imagine you have a notional ground truth model. This is how, if you were to model everything perfectly, you had all the appropriate equations inside of that differential system, that you would have it in a form that's similar to the one that I'm writing. But often we know maybe some aspects of the dynamics and we're missing the other piece of it. We know Z matters, but we don't know how to model Z. Maybe we put in Z tilde. We put in an approximation for that. The fact that I approximated it is where I'm going to get this difference, and that's the model form error. Model form error is in the equations themselves. I can still solve that. The green dashed line is going to be the model results. The data is going to be what I'm trying to fit that to. And if there is a large model form error, then no matter how hard I try to calibrate, I'm never going to get that model to match the data that I'm seeing. So that's going to leave me with the discrepancies in the observable space. Model discrepancy is the difference, and to be careful, it's not the difference with the data, it is the difference between the filtered trend of the data. And all of this, in addition to model form error, parameter uncertainties, data uncertainty, and numerical errors are all should be captured, properly calibrated as well. The uncertainties properly calibrated, integrated for the model predictions. Okay. So in 2020, just kind of keep this around because the work at MIT with the Julia lab showed a great example of how model form error corrections using a neural network can give you a general sense of the trend around the world very rapidly. So while I was trying to mechanistically design that in New Mexico for one state, what the Julia lab was able to do was give a relative sense of the effects of quarantine around the world, which is really quite impressive, right? And so this is great. The challenge here, though, we do have to be careful is we can't actually qualify this for high consequence applications because there's still large model form error in there. There's still, it's only capturing quarantine. It's not capturing all the other effects in isolation. And so what we want to do is actually compare it to that agent-based model. So earlier I said I wasn't capturing the effects of quarantine and isolation. I wasn't able to capture the complexity of the contexts, right? I wasn't able to capture all those localized nuances of each regional complexity, but I want to preserve that there are biologically consistent parameters in how the disease is spreading across the population. And so what we're going to do is we're going to actually put those neural networks in that are specific to exaepi, that exascale implementation with multiple layers of multi-scale interactions for the spread of the infectious disease. I'm just going to put in the neural networks where I have the localized specificity for each regional complexity. This way I want to focus on globally calibrating the parameters. I said I was going to try to speed this up and run through this, but I apologize, I don't think I am. Okay, so what does this look like? And again, I emphasize I'm only going to show the design. I'm going to show you what calibration challenges we're going to have in front of us and what our next steps are to close us out in the last couple of minutes here. So I want to remind you of those first two classes, person-to-person transmission, the probability of transmission. I can capture, I can relate between the two models semantically. Mathematically is a different context, but we can start to build that up semantically. Calibration will tell us if we're doing it mathematically. I can capture the latent incubation, infectious, asymptomatic, and scaling factor for the asymptomatic population between both models that have the same semantic interpretation. The contract probability table, that's embedded, that's hard-coded at the compiler level. I'm not going to access that at runtime, so it's not something I can target right away. So it's actually a better use of me putting a neural network in there to allow the flexibility for it to shift as needed or find the time-varying relationship to that agent-based model. Same is going to be true with the parameter classes for mitigation options. And so the lockdown and my percentage of the population that's symptomatic and choosing to self-isolate. So what have we always done with these models before? So the state of the art really is hand tuning. And so getting in there and finding the right parameter combinations that get you in the ballpark is where we tend to start, right? Because every optimization problem, calibration, this also being true for, right? Every optimization problem is easier to solve if you start with a good initial guess, right? You don't want to be in the ballpark and not make the solver work too hard for you right up front. So I've got this in the ballpark. This was considered the ballpark for me. So I hand-tuned those X-epi parameters and got them as close as I could. But what I'll emphasize on the left here, when I have the infectious symptomatic population for the Bay Area of California, during the first wave of when the pandemic started spreading for that population, starting in February 1st, lockdown happened on May 19th. That was 48 days later, what I'm modeling. The way the model's going to do this is like automatically. Lockdown happens, my population, and there's a percentage of folks that are going to self-isolate. There's a percentage of folks that are compliant, but it is very consistent. People are much harder and much more complicated. This is not capturing COVID fatigue, if you remember that being a thing, right? Where some people are willing to be very compliant early on, it just starts waning. You're like, I am done with this, right? And that level of complexity is not captured in the way that we model it. And so we'll be able to capture some of those nuances by a well-placed neural network inside of there that allows for the time-varying complexity of how people really truly behave, giving us an opportunity to share that with our developers of the agent-based model to ask if they might want to adapt that functionality a little differently based on our insights we can gain. The other one here is on the right, we have the disease-related deaths. I am perfect until lockdown. Lockdown does not cause that differential in the data in my model. It can't. At lockdown, the people who are sick, right? There's no reason I should see a delay in that separation. So what it doesn't capture as well is the fact that the recording requirements also changed. So hospitals are required to report COVID-related deaths at the same time that lockdown happened. So that's why you're seeing the data go up or the model, potentially, conjectures over here, right? But that is something that deviates from what we're actually modeling and what actually happened, and it could be an interpretation of where that separation's occurring. All right, so again, I'm going to emphasize that every optimization problem is only as efficient and potentially as good as your first initial guess. So I'm also going to see if I can get my ODE model within the ballpark of the agent-based model to start. I'm going to put a neural network in there, and I'm going to put that neural network in there to learn and calibrate to these parameters. But all the disease parameters, I'm keeping consistent. So the probability of transmission, latent period, incubation period, that contact matrix, though, is my greatest source of model form error right now. So you can see those look like the trends are relatively consistent between the state trajectories. They're on very different scales, extremely different scales. That means that my contact But the way I'm modeling, the average number of daily contacts is wildly off. But I'm in the ballpark for the trend, which is still a good place to start. So what did I do? The other aspect we have to work on is that initialization of the neural network. So we can do a random initialization of the neural network, use the UDEs, they'll train, they'll find the solution, right? Given enough epochs and opportunities to find those. The other thing is, give it a first initial guess of that function. So for me, I already know, right, what the relative fraction of the population that's expected to recover. I was talking in terms of recovery. And so when we look at the fraction of the population that's expected to recover after being infected, and I take some linear trend within the ballpark of what I have from the reported cases and reported disease-related deaths. And then with my kappa, I'm going to allow that to range. I want it to start early, high kappa. So here it's 55 a day, and allow that to drop off. I would have started with something smaller, but for some reason when I did that, the dynamics just squashed very early on. I couldn't go much smaller than 55 on the initial onset. So this is the design decisions that we are taking into the calibration where we're decomposing local and global parameters. Again, my compartmental model preserves 100 years of knowledge about the epidemiological principles that we know to be true about how disease is spread within their host. They give me parameters that are biologically consistent with the virus itself. And then I'm strategically placing neural networks to give me local corrections so that I can isolate and target that parameterization next. So our next step is to finalize that initialization for training of the efficient UDEs to learn the agent-based structure through that model form error correction. Another big thing we're working on right now is the Bayesian UDE training. So we can start with classic stationary likelihood assumptions, but we have a stochastic system. The noise in my system will be proportional to the amount of infectious people at any given time. So we actually need time-varying likelihoods. And so we're adapting the Bayesian calibration methods to be able to account for appropriate stochastic processes models for that likelihood. And then we'll work through the validation of the UDE surrogates, the ex-epi models, making sure that what we thought was semantically consistent maintains mathematically consistent, and if it's not, we will adapt and report out exactly what those look like. And then we're going to close out with the calibration of the ex-epi global disease parameters for now. And then we can start to isolate that hierarchical going into the local parameters. The reason we want to do that is because often, like if you, in the US, the reporting is going to come out recommendations from the Center of Disease Control. They don't actually make the decisions. Local municipalities make the decisions, state level, county levels are the folks, are public health folks that are actually making the decisions. So that how we understand the disease spreading at a national scale has to work and narrow down into the localized, into the hands of the public health local officials that are deciding whether or not they shut down their city, whether or not they shut down their state, whether or not they keep their schools open, right? And that's going to be specific to their demographics, how dense their population is, how compliant the population is, and other levels of complexity. So we want to be able to isolate that parameterization so it can not only be specific to different regions, but also run on their laptops, because they're not going to have access to Perlmutter at NERSC or Aurora at Argonne, right? Okay, well, with that, I'm going to close out. I maybe saved us 2 minutes. I tried, though. Thanks.
Test. Okay, great. Okay, so welcome everyone to the last but hopefully not least talk of the SciML track for today. I want to start with just a quick introduction of myself. My name is JuliaCon and I am currently a PhD student at the University of Augsburg in the chair of mechatronics. And, sliding off. There we go. Okay. And I want to talk about our package MeshGraphNets.jl today and our adaptation of that graph neural networks-based methods to a neural ODE. And for starters, I want to show you one of the use cases that was in the original paper of MeshGraphNets, which was published by Google DeepMind. And this is just the example of an incompressible fluid dynamics. So you can see just fluid flowing from the left to the right around that white cylinder. And I just want to show you the results of a ground truth versus the prediction. And you always see these kind of fancy animations and you think, okay, well, that looks pretty good. But the questions that I ask myself is, how good actually are these results? How good is the accuracy? And how can we use this method if we want to implement it in an industrial use case where we have more stringent requirements to precision? And that is why we developed our package. So I'll just start with a quick introduction. So what exactly are mesh graph nets? So mesh graph nets are a graph neural network. So at the base layer, it's just a neural network approach. And the idea is that you have a spatially distributed system. So for example, the example that I showed at the beginning is a spatially distributed domain. And you can represent that domain with a mesh, as you saw, and you can translate that into a graph. And like a neural ODE, you substitute the differential equations with a neural network to speed up the process mainly. So these are designed for surrogate models to speed up the process of simulation. You then have the quantities of interest in the introductory example, the velocity in x direction at the nodes of your graph. And you can interpret it as the mesh or the graph is used to propagate these node features along the edges of the mesh in order to influence nodes further down the graph. But I will dive into the detail on the next slides, where I give a quick introduction of how these mesh graph nets actually work. So they are based on the DeepMind called it encode process decode architecture. So in the first step, the encode process is just there to translate our features from the physical space to the latent space. And that is what you have then in the graph. I will update the graph on the right so you can follow along. So there you have the node features, as I mentioned, and the edge features. This is just to have the relative vectors and their length. So you have the relation also as an input of the system. Then in the first step, you update these edge features according to their connecting node features. So you just take an edge, you take the nodes that are connected to the edge, and you accumulate these features and push it to a fully connected neural network. And in the second step, you take these updated edge features, and if you look at the circled nodes, you take all the incoming edges and accumulate these edge features that were calculated in the previous step and update the node feature of that node. And you do that for every node in the graph. It's just for a representation purpose. That I drew the arrows to only one node, but you do that for all the nodes simultaneously. And then you can repeat these steps. So this is the so-called process stage with the message passing steps. This is just a hyperparameter of the system, so you can interpret the message passing steps, the number of message passing steps, and how you want to influence the nodes further on the line. So the more message passing steps you do, you can imagine the further down the graph you're influencing nodes in the same time step if you have more message passing steps. And in the last step for the decode stage, this is where we just do the reverse of the encode stage. So we want to get back from our latent space to our physical space, so we can get to our physical quantities of interest. And then we can calculate our next state. It is important here to mention that in the original implementation of mesh graph nets, there was a fixed time step learned into the system. So the result of the system was not the state derivative, but the state itself. So that was one of the adjustments that we made that had to be done in order to include it as a neural ODE, so that the system as an output has our state derivatives in other states. So, just a quick introduction, since we're at the SciML track. I'm pretty sure most of you know what neural ODEs are, but just as a quick introduction for neural ODEs, they're basically just you have a neural network that you use instead of your physical equations, or you calculate your next or your state derivative on the neural network, and you can use a numerical solver, so the network doesn't have to learn all the numerical the stuff the numerical solver has to do, and you make the learning task way easier, and can use different solvers for different applications that you have, which we'll see later. Now the idea of the package is that instead of just a normal neural network, we plug in the mesh graph nets into the block shown here. And that means we can not only have the machine learning aspect of the approximation, but we can also integrate the physical knowledge that I previously showed because of the graph structure that we incorporate into our system, and can thus incorporate the knowledge, the physical knowledge, into a system to get a better result at the end. And this is basically what is shown here. So now we can use the numerical solver to get the next state of our system, and that means we can, for example, use a solver-based training, so we not only have to use a derivative-based learning approach, but we can also incorporate a solver to our learning process. And we can also use different solvers. For example, if you want to use adaptive time stepping, that's possible. Or based on your requirements, maybe you want to use an implicit solver if you have a stiff system. That's all possible in this design. Okay, so for the industrial application that I want to present today, I have a quick graphic to show. So the underlying model that we use is the model of a hydraulic brake system, as you can see here. And the model is basically comprised of the most important part is the pipe in the middle, as you can see with the red dot at the top. And that is where the most of the calculations are, because the idea is in this model is just a simplified version, but you have a pressure wave at the left. These Pac-Man looking guys are just boundary conditions. We can ignore them for now. And you initiate a pressure wave into our pipe, and this causes the wave to travel across the pipe. And the pipe itself is, like we've already seen in a talk before, is just a spatially discretized 1D model, and consisting in this case of 115 cells. And we have further look at this. In our case, if we want to incorporate it into our mesh graph nets JL library, it's pretty convenient because we have the necessary spatially distributed domain here, so we can just set our nodes into the and into the centers of our cells. Cells more or less because we're 1D, but let's keep it at that, and connect them and have a one-dimensional graph. And we can use our approach. The representation for 5 cells is just here for easier understanding. Like I mentioned previously, in this case we had 150 cells. It's just for easy understanding. One slight adjustment that we did when I previously mentioned the boundary conditions, to help our network a bit, we can take advantage of the mesh GraphNet structures and try to enforce some boundary conditions into our system. So that is what we did here. So you can see on the left where the input of our system is, like I mentioned, where the pressure wave is initiated. We have the pressure as a constant input because that is what we tell our system what the input is. And on the other side, we can set our mass flow to 0 because we want to tell our system, okay, there is no flow going here because the pipe is closed there. So if the pressure wave travels through the pipe and collides at the end, it is reflected back. That is basically what this this tries to tell the system. So now for some training and evaluation data, like I previously mentioned, we had 150 cells in our system, which consists of pressure and mass flow. And on the right side, there are just some plots that show you one example trajectory of our system. Here, I plotted the wave for cell 25. Here's for 75 and for 125. This is just for the later plots that I show you, that we can have a rough estimate so that we have the start of the pipe, the middle of the pipe, and further down the end of the pipe. So we get a nice visualization of the travel of the pressure wave. Yeah, like mentioned, the same goes for the mass flow. So we have mass flows also for the 3 cells that I just mentioned. And our input data to generate our data, we just use the jumps in the pressure wave of 0.8 to 2.1 bars. So if you start at 1 bar, in this case, and we just jumped to 1.8 and 2.2 bar, and this was our data, and this was then split into training, test, and validation data, and everything that you'll see in this presentation was done with a TZ5, so the training as well as the evaluation of the system was just was all done with a TZ5 from differential equations. So let's look at the results. At the first step, what we did was we tried to train our system with just the derivative-based method. So at the first glance, we took out the solver, and we wanted to see how well does the system perform if we're just giving it the derivatives of the data. This is what you can see here in blue in relation to the ground truth data that you can see in orange. And you can see that, well, it's not bad. So the system kind of gets the idea of the pressure wave that travels through the pipe. But we definitely could be better, could do better, especially if we look at the start of our system. This is just zoomed in on the first 2 jumps, or the first 2 bumps in the slide that I showed previously. And here you can see, well, there's definitely some deviation at the start that we don't want. So what we did next was we tried our solver training, because now in our architecture we can do that. And what you can see here is when we trained our system with the solver in yellow, so it's a much nicer fit. And it is important to mention here that we trained our solver only on this part, so only from 0 to 0.085 seconds. And then what we wanted to see was how well does our system extrapolate if we then look at the trajectory that I showed before, so the 0.41 second. This is what is shown here. So this is just the comparison of the derivative-based training in blue again, and the training that we did with the solvers. So the reason why there's a plus at the bottom right is because we first trained with the derivative-based training and then on top trained with the solver-based training afterwards. And what we can see here is, especially at the middle cell and the cell further down the pipe, the solution is pretty good. So we can quite accurately match the ground truth data. At the start, you can see a bit of a deviation. But as you can see here, if we remember what we trained our model on, mainly the first two bumps here in the ground truth data, you can see up until there it's better, and then it just loses the accuracy further down the plot. But that is quite a good result for just training on the first part of the trajectory. The same also applies for the mass flow. I just showed you only pressure waves for convenience sake, but here just so you know, the system also predicted our mass flow, and here you can see there's the prediction with our solver-based training is quite a lot better than the prediction of our solely derivative-based training, but with the same error as I showed previously in the pressure. But here it's on the other side, so on cell further down the line, the mass flow is better in the first two bumps, but gets a bit worse afterwards. But also it has a pretty good approximation or extrapolation of the trajectory that it didn't see. So now to quantify a bit what we saw right here. This is just the cumulative mean squared error of our test data. So what I showed you was all test data, so there was no nothing of these pressure jumps was seen by the surrogate model, and this is the cumulative MSE over the whole test data. And as you can see here, the numbers also speak for the approach with the derivative plus solver-based training, that we have a better solution. Now I want to give a quick outlook to what is also possible, because this was a very simple use case. If you know a bit about the model, it's not that difficult. So the main goal of the mesh nets that we can simulate our system faster was not really given, because the system itself is not too complex. So we were around the same simulation time, around about 30 seconds. That is why I want to show you a quick example of another industrial use case that we implemented our mesh graph nets for, and that is a cabin model. So this is just a two-dimensional slice through a vehicle cabin, and you can kind of identify the seats. And similar to the pipe, it's also discretized in these finite volume cells, but this time we're in three-dimensional space, not only one-dimensional space. So we up the dimensions of our system, which is possible because we just have to define our mesh or our graph on three-dimensional plane instead of a one-dimensional one. And for the results that I want to show you, we're focusing on just that type of cell, just because the system has 400 cells, and I don't think anyone wants to see 400 plots of solutions. And the reason why I chose this cell is because that is one of the more important cells for the user of this model, because that directly correlates to the comfort of our driver, how hot or how cold he feels. Like I just mentioned, we can then use a three-dimensional mesh to apply our method. And for our data that we're using, we are using heat up cycles. So the data consists of actively heating up the vehicle cabin through a HVAC system. So we're actively blowing hot air into our system. And the main goal is to try to predict the temperature of the cells. So what we see here are similar results to the hydraulic brake pipe that we've seen before. You can see here in orange is our ground truth data. The reason why we have a green strip around the ground truth data is because that was one of the requirements that we had. We should not deviate from a 1 Kelvin plus minus from the ground truth data. This is why the green plot is there. And as you can see, if you just use the solely derivative-based training in blue, the solution is not in the green area of the plot, which is not what we wanted. But if we also try our approach with solver-based training, you can see in yellow, then we're matching our ground truth data actually quite good, and that is exactly the results that we were looking for. And since I already spoke, now we have a way more complex model than before, so the numbers are a bit more interesting. If we look at the simulation time and the cumulative mean squared error, so the original model for our simulation was around 260 seconds, and with our surrogate model with Meshgraph nets, we only had a 30 seconds simulation time, which is a big improvement. And like previously in the pipe for the hydraulic brake, we also show that oops, that is my mistake. I messed up the numbers. They should be the other way around. The derivative-based training is, of course, the one with the 4.3 mean squared error, and the derivative plus solver-based training is the one with 0.596. So just a little mix-up. So for our conclusions, what we did was we formulated the Meshgraph nets network as a neural ODE to make it possible to use these kind of solver-based trainings and evaluation methods, and we showed that this is also the way to improve our results of our solution. And we showed 2 applications of our industrial use cases where we applied the method and had results that were very good. Our next steps are we want to try and make use of a more complex hydraulic brake model, because, like I mentioned, this is a quite simple model, but the reality is not like that. The models for hydraulic brakes are quite a lot more complex, and without going into detail, we want to implement the approach for the more complex models and see if we can achieve similar results to our cabin model, which was also quite complex. And this also means that the pipe model can be extended, because one of the main advantages, since we have these graph-like structures in Meshgraph nets, we can try to expand our graph if we change our spatial domains. So for example, if we make our pipe a bit longer, or if we change the layout of our vehicle cabin, then we do not have to retrain our system, because we are not learning a global solution, so to say, but the local relations between the nodes and the features. So it is possible to evaluate our system without retraining it. And that just falls under the last point that is written here, which is the further development of the package, which you can find under Meshgraph.js release package or under that QR code. We're always welcome for issues or PR if you try to use it, and maybe if you like it, leave a star. That would be great. And with that, I conclude my talk, and I'm glad if anyone asks any questions.
Maybe a technical question. Why do you use Ceturas? Because I think your problem, at least for higher number of nodes, will be stiff, and Ceturas is a non-stiff solver, right?
Yes, that is correct. We tried a lot of different solvers, and it is always a trade-off between the training times and what you try to achieve. So the training process with implicit solvers is not really possible in the current ecosystem, because if you try to use implicit solvers on the GPU with Zygote, is such a huge model, because it has a lot of parameters, then it gets quite tricky. So for the training, it's not really feasible. That's why the solver got used. But what we saw in the simulation times is that although the DZ5 is an explicit solver, because of the adaptive time stepping, it was able to match the data quite well, although it's not a stiff solver.
Okay, thank you.
Is it possible to extend this to, let's say, different coordinates than the nodes in the mesh that you have now? Because, for example, the first example, or the first break, I think it was, seemed to be quite low dimensional in dynamics.
The structure of the mesh you can always adapt, because, like I mentioned, the solution that, or the system that I learned is not the global one, but a local one. So changes in the structure are always possible. It's just a matter of, are the results still good enough for what you need or what you want?
Just a question on how would you define the mesh typically for quite complex 3D geometry?
In this case, it is, well, most of the times it is given by what you can actually get from the data. So for example, for the cabin model, our only approach was, like I showed, where we used the center of our cubic cells as our nodes and connected them, because these were the only points where we could sample of quantity of interest in the original model. So that is one aspect that you're limited to. If you have more freedom there, so you can more arbitrarily choose, then there's also the possibility of hyperparameter tuning your mesh layouts, or for example, what in the original paper was dynamically remeshing if the accuracy is not good enough. But in this case, we were just limited to what you can get from the model. And that is most often not the case, that you're limited to such things.